Hello. Good morning, everyone. We now begin day 2 of the International Conference on Emerging Frontier in Sustainable Functional and Advanced Materials, organized by Physics Department of Shivaji College, DU, sponsored by ARF. For this session, we are honored to have Dr. Bharti DTU as our chairperson for this session. Now, I would like to call Dr. Neeti Goel ma'am to chair this session further.
Thank you, Sanskriti. So today we are going to the second day of the conference, and to start with, we are going to invite Dr. Ajit Kumar Batra as the invited speaker. He is from University of Hyderabad. And he will be giving his talk on stabilization and current driven dynamics of Skyrmions in chiral magnetic materials. So welcome Ajit Kumar Batra. You can start.
ये वाला तो जाएगा ना ये लेजर ना ठीक 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 है very good morning to all of you. Thanks Dr. Surender and the team for inviting for the conference. So I am going to briefly talk about the stabilization and current driven dynamics of Skyrmion in chiral magnets. So you have known the magnetic materials. So I will briefly introduce what is Skyrmion and what is chiral magnet, in the sense these are the typical category of magnetic material. They have lack of inversion symmetry. So spin orientations has a certain behavior. So you have topological spin structure, and that can give light to Skyrmion that we are going to see on this typical material. So before going this, so this is the research activity in our group. What we do is study the highly anisotropic thin film with perpendicular magnetic anisotropy, both fundamental point of view and for applied research, and Skyrmion dynamics, that is the part of the today's talk. And also we focus on understanding magnetic ground state in novel Heusler alloys. So before I move, so these are the people who involved in this work, some the students and the collaborators from NPL, and these are the funding agency who generously support our research. So the content of the talk will be, I will introduce the Skyrmion in upcoming storage technology. What is the advantage compared to the domain dynamics, and what is Skyrmion as concept, how do we detect, and what is the application of Skyrmion, and our own contribution both experiment and simulations, mostly focusing on simulating this magnetic skyrmion. How do you can stabilize? What are the typical parameters which allow us to stabilize the skyrmion? And the skyrmion in spintonics, what is the fusor in this directions, and summarize in the finally. So if you look this our semiconductor technology would follow the Moore's law, and it says the number of transistor and microchip doubles every 2 years. So this is like transistor count on the y-axis, where the x-axis is the year, and is already in the verge of saturating. So you have got already in the verge of saturation. So you cannot just reduce the size of the transistor to accommodate more number of transistor in a chip. Rather, you have to look for the new paradigm. So new way of storing the data, and that is what magnetic material can allow to do. And the skyrmion is one of the promising technology which can allow to have a denser data. So existing storage technology, which is again based on magnetic material, that is called domain wall-based magnetic memory technology. So typical bit size here is 20 to 30 nanometer size. You want to reduce to have a better density, you need to go to the size, the bit size is lower. What does the bit size mean? This is the domain which will allow you to write like 0 or 1, that is the size of the bit. So in existing storage technology, again I will briefly discuss in the next couple of slides, which is stabilized by external factor, whereas skyrmion is inherently stable. There is an inherent stability due to the topological properties of this skyrmion, and is prone to data loss, well as is highly robust, and it allows you to denser data storage because of smaller bit, and this is more stable. And that means you have 80% less space compared to the existing storage technology, and cost is also much reduced. So briefly look what is this current technology deals with. There is based on the domain dynamics or domain wall motions using current. So this is here how the ferromagnetic material is uniformly magnetized. Then it is called, this particular region is uniformly magnetized region, this is called the domain. So this is domain pointing from left to the right. This is another domain which is uniformly magnetized region of this magnetic material, where all the magnetization is aligned in the particular directions. This is from right to left. So this is a domain 1, this is domain 2, and in the crossover, the boundary between these two uniformly magnetized region or the domain is called the domain wall. And that basically decided by your competition between the exchange energy and anisotropy energy to see what is the size of the domain there. Okay, and depending on the kind of magnetic material you have, this is all random domains. Different color basically signifies the different directions of magnetizations, or you have magnetization in the vortex states. You have, this is the core, is the vortex states. So this is again is two oppositely aligned magnetic domain. This is the transverse domain. So two domains magnetization like pointing to each other, and there is magnetization in the domain wall going away from this easy directions, then your domain wall. So in current technology, basically you want to push this domain wall so that you write 0 or 1, and that's using current density. Where the skyrmion can have less current density can be used. So you briefly see that. So this is what the current, this domain based data technology. So this is longitudinal or in-plane magnetic recording. So magnetization of the beat is in the plane. So this is one beat. Basically this is the beat length. So 0 or 1, that's 1. So perpendicular magnetic recording, like you have in the plane, you need more space to store the same data. You have magnetic recording is perpendicular. You have in the same space you have more data can be recorded, and this is stable in high density. So this is what doing with domain dynamics. But while going to this skyrmion based, this is what we are looking at. This is what skyrmion can be beneficial compared to the existing domain technology. So this is what domain versus skyrmion. So what is domain? This is a uniformly magnetic region, it's called a domain, and the boundary between two uniform regions is called the domain wall. So ferromagnetic ordering is a collinear spin configuration. All the spin are collinear to each other. Whether you look for a skyrmion, which is a non-collinear spin configurations and non-coplanar also. So the spin are twisting in what happened? Spin are twisting in all possible directions. So you have a core which is pointing down, and the boundary which is pointing up. And between this core and boundary, spin are twisting in a different way. So this is the way non-collinear spin configurations. That is skyrmion. And energetically, this is more stable. But once you stabilize this, it is a topologically protected one. It will be more stable to any kind of perturbations. So this is what Skyrmions is proposed in 1961 is a magnetic quasi-particle. So this topologically protected spin configuration unlike domain, that means small perturbation like field and external things, still this domain, the spin configurations of the Skyrmion will be stable. This is a non-coplanar and non-collinear spin structure. So this is the two example of, one is the block Skyrmion, another is the nail Skyrmion. And this is a very recent development. This is 2009. This is first experimentally is discovered in MNSI. This is a block type Skyrmion with a size of 19 nanometer. So still people are looking at how you can stabilize this and stabilize at room temperature. And what is the typical smallest possible stable Skyrmion can be used. So that can be used in the data storage for 0 and 1. That we briefly show that. So this is an array of Skyrmion, like all possible array of Skyrmion. So you can have like 0 and 1 the way you want, and you can use the current density to move the Skyrmion like it is in domain, and the rest track memory. So this is a magnetic Skyrmion. This is a non-collinear swirling spin structure. This is how the spin configuration rotates from the core to periphery. And these properties could be small in size, and this can be controlled by magnetic field and current density. And this topological protections, like this is a donuts, and then it can be topologically mean this you can convert into continuous deformation to a coffee mug. So these are two topologically same material. So it's you cannot deform this one. So topologically more protected one this. So this is an application could be in magnetic memory devices, logic circuit. Like this is what like 0, 1, 1, 0, 0. This can be written like same as a domain. Or you can use it in different gates like OR gate, AND gate, and NOT gate by moving the Skyrmion the way you do within domain dynamics. So this is like what's topology mean? So it's topology protected. This is one peculiar behavior of Skyrmion. So this topology is a property of geometric object. This is a typical definition in mathematics used that are preserved under continuous deformation such as stretching, twisting, crumbling, and bending. That is without closing holes, opening holes, tearing, gluing, passing through it. So two topologically same material are what is it? You have donut and a coffee mug. Because without tearing and hole gluing, you can transfer from this to that one, or you can come back from this coffee mug to the donut. Whether this Mobius strip, which is this one, the two are topologically different one. So in order to go from one to here, we have to cut a tear, then only you attach, then you go from one to another. So these are the topological protected. So this will stable when you apply external magnetic field for large enough, or the other will not able to stable. So that is the beauty of this topologically protected spin structure for Skyrmion. So when they say you have a ferromagnet, which is like collinear spin structure, it has the lowest energy in magnetic ground state. But if Skyrmion spin are non-collinear, non-coplanar, they have a higher energy. But by some means, if you stabilize the Skyrmion, this is quasi-particle, then it is more stable than the ferromagnet because it cannot be disturbed using small perturbation, because coming from Skyrmion to collinear ferromagnet, you have to overcome this large energy barrier. They are much protected by the large energy barrier, so Skyrmion will be more stable compared to the ferromagnet one or domain one. So that is why topological protected can give advantage for the Skyrmion. So important. What is the importance of this properties of applications? One is the size, because you want to have denser magnetic recording, stability at room temperature, and what the factor basically decide whether Skyrmion will form or not. There is a phase boundary, a phase diagram. So this energy term that is involved with the G1 energy term. What is the strength of the external magnetic field? If you apply a magnetic field, the G1 energy, see how much energy that you will have to always try to align. For the exchange stiffness constant, which is basically related to the energy density required to twisting or rotating the spin, and strength of this is Diagonal-Moria interaction, that is called DMI. So the last two terms let's briefly talk about. So the exchange interaction, this is an Heisenberg exchange interactions, and these two terms J and this exchange stiffness are correlated, directly correlated. So if you have an Heisenberg exchange interactions, always align parallel spin, parallel to each other, so energy is minimum in this case. But if you have a DMI, this is the Diagonal-Moria interactions, there is again uniqueness in some system, having in lack of inversion symmetry, that follow or that prefers to have an orthogonal alignment of the spin. So one prefer the parallel alignment or collinear structure, where other allows orthogonal line structure. The competition between these two will give you a twisted spin structure. So in order to have a Skyrmion, DMI interaction is must in the system. So is the competition between how much the exchange energy how much the DMI interactions, and how the Zeeman energy by applying magnetic field in a region of this 3 parameter and as a function of temperature, you stabilize the skyrmion. And that I will show you how the skyrmion evolves when you change this parameter in our dynamic simulations experiment. So this is the family of different kind of skyrmion. It is like you have an anti-skyrmion, which is basically an anisotropic version of a skyrmion. This intermediate skyrmion, this higher order skyrmion. I mean, skyrmion can be defined with a skyrmion charge or skyrmion number. SK1 for the skyrmion is 1, anti-skyrmion is -1. Higher order skyrmion could be +-2, +-3. This is the meron is the basically in half skyrmion. Skyrmion number will be half. Bimeron means 2 different half skyrmion. And you have biskyrmion, there is 2 different skyrmion. Skyrmionium, you have skyrmion and anti-skyrmion together. All kind of structure people could predict, and also there are a lot of experimental research and developing in this regard. So this is what our own simulation we did. This is the material. This is we have a like block skyrmion. So it's like block magnetic domain wall. You have block skyrmion where the core and periphery the spin rotate tangentially. If you have go to different kind of material system in thin films, you have a nail skyrmion where the spin rotate from the core to the periphery radial directions. That should define whether you have a nail skyrmion and the block skyrmion in the system. And this is what detecting skyrmion people have done. They're using low temperature TEM, which is widely used. So this is basically giving confirm or direct imaging of the skyrmion picture. And also there is seen using this is different material system, PMNP and FEG showing block skyrmion. And then other technique like you have small angle Newton scattering, magnetic force microscopies also people have used to show this one. But there are also indirect measurement, which is like DC magnetization, AC susceptibility, topological Hall effect can allow in the lab system to also detect skyrmion, such as you have a DC AC susceptibility as a function of field you applied, you see a clear dip in this measurement, which basically says the boundary between where skyrmion is created and skyrmion is annihilated in the system. And we use this lab scale method to investigate skyrmion in our system. So one of the most interesting systems that you have used is the manganese based alloy. This is COZNMN, which is in a very promising skyrmion host. It has very different magnetic ground state, such as ferromagnetism, antiferromagnetism, spin glass. And this like total number of atoms in the like X, Y, Z is 20. And small variation on X, Y, and Z, the magnetic properties changes drastically. And people have seen this different technique, the skyrmion in the system. And one of the beauty of this one is that they have a Curie temperature higher than the room temperature. So keeping application point of view, we started preparing this in collaboration with NPL, and we have seen this in polycrystalline sample. We have a clear dip in AC susceptibility where you can clearly show that we have a skyrmion pocket in this field range. Then we move to another sample. This is like 776. This is total. So you simply move to 884 system, and we could see the TC is 340K, and below the TC again you have a skyrmion pocket that we observe. And in this situation, then we started doing our simulation in 9-on-2 skyrmion host system. And this is the 2 different our own simulation result, which stabilize to show that you have block skyrmion or you have a nail skyrmion. And then we typically use micromagnetic simulations using MuMax software. This is an open source software, anyone can use it. And this is a typical simulation micromagnetic parameter by varying different external magnetic fields so that you can tune the Zeeman energy, action stiffness, and the DMI. We try to see what is the best possible condition where you can stabilize the smallest possible skyrmion. And this is the similar, our result, our own simulations. There is like isolated skyrmion. This is an elongated skyrmion. We have biskyrmion and skyrmionium. This is all we have seen in our own simulations. And this is our fast micromagnetic simulation data. So we start with like fixed exchange stiffness constant and vary the magnetic field. So very at low magnetic field, you have all kind of ordering. What happens like you have competition between this exchange stiffness and your DMI. So DMI is also fixed. So at the very low field, that is you have not, field is low, then Zeeman energy is too weak to polarize background. And then you have all sort of order like you have elongated skyrmion, then domains, all kind of stuff. Once you increase the magnetic field, then the background is more polarized. So the Skyrmion boundary is more now visible. So you have clear isolated Skyrmion started evolving. So your Zeeman dominated transformation from elongated or mixed structure to an isolated Skyrmion. If you increase the field further and further, then it is always try to polarize, but at certain field, because the Skyrmion have a twisted spin structure, and magnetic field is always polarized. So at a higher field enough, you will completely saturate it. The Skyrmion will annihilate. So you started with like mixed structure, then you have an isolated Skyrmion, then you have complete annihilation of the Skyrmion. This is how it see that. So mixed state at low temperature, low field and low exchange, but you have enough 220 millitesla, your isolated Skyrmion start evolving. That is basically competition with the energy term between this Zeeman energy, exchange energy and DMI interactions. At proper Skyrmion is evolve at this particular values of that one further. So then we try to see whether you can change this, we fix this magnetic field where you have seen the Skyrmion, isolated Skyrmion, and vary this exchange stiffness constant. And you see at a very low exchange stiffness constant, again you have all kind of mixed structure. Because exchange stiffness is try to again align parallel to each other. So you cannot stabilize the large ordering of this twisted Skyrmion. Of course, DMI is playing the role. DMI we have kept a fix. So at a higher, at basically very large field, again is most of the case you see isolated Skyrmion, but a well-defined one with a pure boundary will evolve in the system. So you further move in, what you see that you have D for interfacial DMI. That means you have a system bulk. If you go with thin films, you can introduce this DMI in the system. And we see similar behavior of like Skyrmion appearing at like mixed states, then isolated Skyrmion around external magnetic field of 200 millitesla, and then a very large field, you completely, this ferromagnetic ordering, everything is polarized, no twisting of spin. Because DMI always you need, so the spin is twisted. And exchange is always you want to have large domains, because that is a domain, because increasing the domain energy of that term. And this is again the micromagnetic simulation we did for D bulk, and this is for D is like interfacial DMI. Same behavior we see for bulk and interfacial DMI. The situation depends because how much your exchange stiffness and the DMI interaction that is plays a major role. And then what interesting we see, this is the summaries of our result, like if you have what is the Skyrmion size changes with the external magnetic field. So this is our, this is Skyrmion size with the external magnetic field, and this is the exchange stiffness constant, this plot. So if you have very low field, Skyrmion started increasing size. That means at the low field we have mixed states. If field is increased, the background is more and more polarized, so the well-defined boundary is there. So Skyrmion size start increasing. After certain values, then the Skyrmion, then you have magnetic field, the Skyrmion size decreases because this magnetic field will try to, every spin will be aligned, because twisted will not be favorable, because twisting will be having lower preference, so the size decreases. And if that you do see for all values of exchange stiffness constants. But again here you see the plot of Skyrmion as a function of exchange stiffness for B external. So for very low field, Skyrmion start increasing continuously, because you have the exchange stiffness is basically try to larger exchange stiffness, larger will be the domains, larger will be the Skyrmion. But a very large field, what will happen? The magnetic field will try to oppose this one, so it started saturating this one. If low field, it could keep continuously increasing. But in higher field, these two competition give you saturations. Initially they keep on increasing because larger the exchange, larger will the domains, and then the Skyrmion is also increasing because there is basically the twisted spin structure. And then finally very high field, above 200, 250 millitesla, you have saturation in the system. Initially this is dominated by exchange, and this is grow within exchange, and at higher field value, this is again controlled by the magnetic field. So you try to saturate. So in this way, you have see what is the typical behavior of all these three parameters. We can see the stabilized Skyrmion, and we repeat the same thing for our interfacial DMI. And this is a low field where there is no saturations. But higher field you have Skyrmion size increases further, and at particular value of magnetic field, critical field, that started saturating. And then this is our typical optimization parameter that you find out. So for the bulk and the DMI, so this is in the combination of, this is around 28 to 280 millitesla. We have roughly around isolated 50 nanometer size Skyrmion that you can put stable. Again, also we have scanned this for different value of DM. This is for DMI, which is basically follow orthogonal spin structure, twisting of that one. Very low DMI, which are not able to compete with the magnetic field or exchange. A very large one, also the Skyrmion will be not stable there. So in the intermediate range of this DMI, for different value of external field and the exchange, you have nearly isolated individual Skyrmion of the order of 60 nanometer that you have seen. So this is basically our result, and we are now further we are oblique field that we are applying, so that we can move the Skyrmion, see the Skyrmion is more stable or not, different magnetic field. Because now the magnetic field we have only for one particular directions. Now magnetic field we are arranging in the XY plane or XZ plane to see how going to affect the size and stability of the Skyrmion. So this is application of Skyrmion. So that is, you have this Skyrmion based memory and data storage, like you have 0 and 1, and this is your how you sense the size of Skyrmion with 0 or 1 is written, like a magnetic domain state. And this is what the logic computing devices operations. And also people have seen the Skyrmion in racetrack memory. Racetrack means just like your car racing on a track. So the car is moving continuously. Here you can move the Skyrmion using current, electric current density, and that current density required for moving a Skyrmion is 2 to 3 order of magnitude lower than the typical this domain wall based one. I don't know, can we run this? This is how the Skyrmion is like in application of magnetic field, the Skyrmion is moving, and that moves much faster than the domain wall, and the current density basically required less. So the heating effect will be very, very lower. So this is more energy saving, the low power electronics can be built using this Skyrmion spintronics. Can you go to the next? Skyrmion are smaller, more robust, require lesser driving current. And this is the summary of what Skyrmion can do. Is a small in size, very small, few nanometer, topologically protected, stable. It's robust to external perturbations. It's energy efficient, current density required less, and an easy maneuvering, like you can have different material parameter, you can stabilize this Skyrmion. So this is like, hence Skyrmion are the future of data storage and information processing technology. And this is, thank you very much for this one. This is our picture of the campus at the University of Hyderabad.
Thank you, sir.
Yeah.
So, is there any questions? Clearly explained the difference between the domain and Skyrmions. It was very nice. So, no questions?
Maybe they don't understand anything. Who knows?
So, it's time to felicitate our invited speaker. So, you were asking something? Okay, okay, sir. But sir, because of this, the photograph is not nice because alphabets are coming on the face.
Thank you very much, ma'am, for inviting me. And first of all, I would like to thank all the organizing committee members, especially Dr. Surendra Kumar, for inviting me and presenting my work. So basically, today I'm going to give the talk on the photocatalytic performance of these compounds. These compounds are dysprosium chromate, rare. No, I think you can hear me. Yes, no need. So the compounds that I will be discussing are dysprosium, rare earth chromates, and here Re is 3 rare earth elements, gadolinium, holmium, and ytterbium. So we have prepared their nanomaterials, and we have also prepared their nanocomposites with reduced graphene oxide. So before I go further, I would like to introduce my university. As it has been told that I come from Department of Physics, Chaudhary Charan Singh University, Meerut. So this is a very fast-growing university. It has been recognized by world-class ranking. For example, the university has come in the Times Higher Education ranking in the band 1200 to 1500. It has also been given QS ranking, 222 ranking in Southern Asia, and it has been awarded the prestigious NEC A++ grade with a CGP of 3.66. It has been awarded an IRF rank 41 among the all state universities. This university has secured 100 crore rupees grant from PM USA, and it is one of the leading universities in terms of patent. Under the government category university, it comes at the 4th place in filing the IPR patent. So there are many accolades associated with university, and this university was established in 1965. It is located in Meerut city of Uttar Pradesh with a lush green campus spanning over a 220-acre area. It has 22 UGC sponsored and 35 self-financed programs. Almost 400 colleges are affiliated, and it caters the need of 9 districts in Western Uttar Pradesh, and almost 4 lakh students are associated with this university. So in my presentation, I would like to give introduction why we have the water that gets polluted, what are the sources of water pollution, and what are the remediation for treating water, wastewater treatment basically. Then what are the materials that are being investigated nowadays, and I would discuss about our materials that we have synthesized and characterized for wastewater treatment. So as we know that water pollution is a major concern nowadays. Even day before, 2-3 days back, I was reading a CAG report in which it says that 55% water of Delhi is not suitable for drink. So water pollution is one of the biggest problems that we are facing right now, and water pollution from organic dyes is a major environmental problem, especially in the areas that use dyes in textile, paper, leather, plastic, and dye manufacturing industries. All these industries use a lot of dyes for making color compounds. So these dyes are designed to be chemically stable, resistant to light and oxidation and microbial attack, which makes them persistent pollutants in water. So you can see here the diagrams that water is being thrown in open, and you can see that water getting polluted due to the influence of different dyes. Almost 10 to 20% of dyes used in textile processing are thrown to the wastewater during dyeing, and 7 lakh tons of dyes are produced annually. And you can see, आप सभी लोगों ने वो खाए होंगे जिन्हें बोलते हैं बुढ़िया के बाल, ऐसे है ना. So that contains a very harmful dye, rhodamine B dye. So that is cancerous. So it has been blocked in many states. So textile industries contribute largest share of dye wastewater pollution. So that's why we need to have catalyst for or materials for this wastewater treatment. So environmental impact is, as on the previous slide, you can see that with the mixing of dyes, water becomes opaque. Therefore, it reduces light penetration, and what it does is that it affects reduced photosynthesis of aquatic plants that are present in water, and it decreases the dissolved oxygen in water. It also makes toxic water. Many dyes and their breakdown products are toxic and carcinogenic in nature. That one of the very simple example I gave to you, the buddhi ke bal. So aromatic amines from azo dyes can cause cancer and mutagenicity. So it has also, by accumulation, it has been observed that the living beings that are present in water, they are also affected by these dyes. So some dye molecules accumulate in fish, algae, and microorganisms, which disturbs the aquatic life. So there is oxygen depletion that is present in water, which is required for the living beings living in water. And this not only affects the living beings in water, this affects the wastewater, also affects the human health. So contaminated water, it can cause skin irritation, allergies, respiratory problems, mutagenic and carcinogenic effects, liver and kidney damages are there. So some dyes like malachite green are highly toxic and banned in many countries. There are several treatment methods for treating this wastewater treatment. So there are physical methods, chemical methods, and biological methods. Physical methods cover like adsorption, in which we have activated carbon, clay, or graphene. They do not dissociate the dye, but they take away the dye with them. So like membrane filtration is there, ion exchange is there. So that's why there is a saying, pani piyo chankar, guru banao jankar. So the same way we treat water, we treat water by membrane filtration. And there are chemical methods like oxidation method, ozone treatment is there, advanced oxidation process is there, and other biological methods are there to treat water. But these methods are very costly, very time taking. Therefore, we need to have a simple method for wastewater treatment. And nowadays we have several types of advanced catalytic methods like photocatalysis, in which light is used to generate charge carriers, and those charge carriers attack the dye, and they break the dye into simpler, less harmful molecules. And there is another method that is used for the wastewater treatment, that is piezo-catalysis. Piezo-catalysis, you know that there are certain materials, if we press them, they generate charges, and these charges are again used to generate radicals, which again attack the dye, and this way the dye can be decomposed into less harmful products. So sonocatalysis there, in which high frequency waves are sent through water, and this is the treatment method, or their combination is also there, like photopiezo-catalysis process is there. So as I mentioned you, these methods generate reactive oxygen species such as hydroxyl or superoxide radicals, which degrade dyes into carbon dioxide and H2O, less harmful products. So in this talk, I am focusing on photocatalysis process. As the name implies, photo and catalysis. Photo means light, and so the catalysis process is through light. And we know that light is abundant everywhere, it is available everywhere, therefore it is a natural process. An advanced method used to remove organic dyes from wastewater using light activated catalysis. And principle of photocatalysis that we should have a semiconductor of suitable band gap which can absorb light with energy equal to or greater than its band gap. So then electron hole pair would be generated. So through this reaction there is a catalysis, and that will absorb light, and electron hole pair would be generated. So all the graduating students, they should be knowing that in a semiconductor we have valence band and we have conduction band. They are separated by the band gap of the material, and if we have the light incident on the semiconductor, and if the light has suitable wavelength, it is equal to the band gap or greater than the band gap, then electrons would be promoted to the conduction band and leaving behind the holes in the valence band. So then these electrons can react with the oxygen available there, and it can convert into the superoxide radicals. Similarly, holes present into the valence band, it will react with H2O, and it will break into the hydroxyl ions, which are super radicals called, and they will attack the dye and they will degrade it. So all sorts of materials are present for this wastewater treatment. We have binary photocatalysts, which have two elements in them, like titanium dioxide, zinc oxide is there. We have chalcogenides based binary photocatalysts like cadmium sulfide, zinc sulfide, copper sulfide, and so on. Nitride based photocatalysts are also there, gallium nitride, tantalum nitride, and graphitic carbon nitride. Then we have ternary photocatalyst also, and in this class of photocatalyst we have one perovskite based photocatalyst, that is my research work that I am going to present. So perovskite structure, I will discuss it briefly. So when we say the photocatalysis, so these are the important parameters. So what should be the band gap of a good photocatalysis? What are its other properties? So band gap energy is one of the important. If the band gap of the semiconductor is in the visible radiation, that it will absorb visible light, but for large band semiconductor it absorbs only UV light, which is harmful also and present in less quantity on the earth, because it is absorbed by ozone layer present in the upper atmosphere. For example, this is a very typical example of a good photocatalysis, titanium dioxide, but the problem is that it has band gap of 3.2 electron volt, which lies in the UV region. Therefore it is active under the UV radiation also. Therefore, ideal photocatalyst band gap should be around 1.8 to 3 electron volts, so that we can utilize the visible spectrum of the electromagnetic radiation. Then surface area is one of the important criteria to choose a photocatalysis. Because if the surface area is large, it means that we have more active sites, there is better absorption of reactants. And that's why nanostructure materials are important, whether they are 1D material, 2D material, or they are 0D materials. Then catalyst loading is also important. If we have very small amount of catalyst, then there will be less number of active sites. And if we have, but as we increase the catalyst content, so reaction rate would increase. But again, that is a problem, because above a certain load, reaction rate decreases due to light scattering and blocking. Therefore, we need to optimize the catalyst dose also. And once we have generated the charge carrier, we should not allow them to mix them together. So electrons are promoted to the conduction band. They should not fall to the valence band again. Otherwise, there would be problem. And light intensity is also one of the factors. Then pH value also matters. Yes. Like if we have defects, then they are beneficial for this photocatalytic reactivity. You can see you can have no, yes, this is the slide. So you can have shallow defects as well as the deep defects in the present, and they influence the photocatalytic performance of the material. So these are the several factors that I discussed here. Now, as I mentioned you, perovskite structure, this is a very important structure, and semiconductor perovskites are very important class of materials for this wastewater treatment. So perovskite structure, it is named after Russian mineralogist Lev Perovsky, and this structure has formula that is AbO3 structure. So nowadays you might have heard perovskite halides, that are solar cells that are giving competition to the silicon solar cells. So they have very real world applications. Because of the following properties, they have large absorption spectrum, their band gap can be tunable, they have large power conversion efficiency, they can be used catalyst for dye degradation, they are used in memory devices, in gas sensing properties, in magnetic refrigeration. So this is the structure of Perovskite AbO3 structure, in which you can see that A ion can sit on the corner of the cube, B ion sits at the body center of this cube, and 6 oxygen atoms form the what we call as octahedra. So there is a BO6 octahedra present in this, but this is ideal cubic structure. In reality, we have the distorted cubic structure, so the crystal structure becomes orthorhombic in place of ideal cubic structure, and when it becomes the orthorhombic structure, we can have distortion present in the structure. So this one distortion is that this octahedra, it either can rotate or it can tilt, or there could be a cationic displacement, and that is very important. If positive ion and negative ions are displaced, so this material become polarized, and it has been seen, as I would show you, that such materials can become ferroelectric also. So they have sort of applications. They can be used for hydrogen production, they can be used for dye degradation, they can be used as a gas sensors, they can be used as electrocatalysts, they can be used for magnetic refrigeration, they can be used for electric refrigeration. All sorts of applications are there. So out of all the perovskites available, we have chosen this material, dysprosium chromate, DYCrO3. It is one of the member of rare earth chromate family. So it has orthorhombic structure at room temperature with PMNP space group. It has several type of distortion present, that is the rotation of CrO6 octahedra, or there could be the rare earth displacement. It has very interesting optical and magnetic properties. It has paramagnetic to anti-ferromagnetic near transition temperature around 140 Kelvin. And but it is not completely anti-ferromagnetic. There is a small ferromagnetic component present in the anti-ferromagnetic matrix because of the presence of spin canting, and it has low temperature dysprosium ion ordering something less than 4 Kelvin, which gives rise to spin reorientation transition. It has a strong absorption near visible radiation. Band gap is around 3 electron volt. It has very interesting dielectric properties. It exhibits giant permittivity of the order of several hundreds at 0.7 megahertz frequencies. It has, so very first report, something around 2015, this material was used because it is a semiconductor with band gap around 3 electron volt. It was used for the degradation of rhodamine dye, but it could be degraded only 53% under visible light irradiation with rate constant of 4.08 into 10 to the power minus 3 per meter. And it is a multifunctional material. Basically, it shows magnetic properties, it shows photocatalytic properties, it shows gas sensing properties. So, for example, in this material, iridium has been doped, and it has been used as a low temperature magnetocaloric materials. And you can see here that magnetocaloric material, as if you were present yesterday also, it was discussed in some of the talk. Magnetocaloric effect is an effect where you adiabatically apply magnetic field on a material and then adiabatically remove it. So with this phenomena, you can decrease the temperature of material. So this is the basis for solid state refrigeration, that is giving competition to the gas-based technology, because gas-based technology that are used in refrigeration, they generate harmful gases. So these materials are important for magnetocaloric applications, and how do we measure the magnetocaloric effect is through these two equations. One is the magnetic entropy change, which is nothing but Maxwell thermodynamic relation for a magnetic material, and another parameter is the relative cooling power. So in this iridium doped sample, very good amount of relative cooling power and magnetic entropy has been observed, but this is observed near liquid helium temperature, something around 0 to 10 Kelvin. So this is a low temperature refrigerant material, not room temperature refrigerant material. In another study, room temperature ferroelectricity has also been observed in this material. So what they did, they prepared two types of material, the same material by two methods. One was the solid state reaction method, one was the solid state reaction method, in which the material was centrosymmetric. It means that the center of positive ions and the negative ion coincide with each other. Therefore, there is no signature of ferroelectricity at room temperature, but in the spark plasma sintered material, there was off-centering between the positive ions and negative ions. Therefore, that material could become ferroelectric at room temperature. It was confirmed through ritual refinement of XRD patterns that the spark plasma sintered materials was giving best fitted with this space group PNA half, whereas the solid state reaction material synthesized that was having PBNM group, and it was fitted with PBNM group, which is centrosymmetric. So therefore, it is non-ferroelectric, but this phase could be made ferroelectric, and the ferroelectric behavior was confirmed through this positive up negative down measurement technique, in which we have observed the reversible polarization, and this reversible polarization was also confirmed through the piezo response force microscopic technique, in which we can see different contrast in the amplitude and phase diagram. So this material could become ferroelectric at room temperature, and it is ferromagnetic. And this in solid state synthesized sample or by synthesized by others like Sol-Gel methods, weak ferroelectricity has been observed near the magnetic transition, as I mentioned you. This material is, it exhibits a paramagnetic to anti-ferromagnetic transition at something around 140 Kelvin. So near 140 Kelvin, there is spin phonon coupling at that temperature. There is a phonon softening around that temperature. So therefore, some signature of ferroelectric behavior is also present near the magnetic transition in this sample. In room temperature, ferromagnetic behavior has also been observed in this compound with iron doping. With iron doping, where we have observed a slim ferroelectric loop at 300 Kelvin also. So this material could be ferroelectric as well as ferromagnetic at room temperature. Therefore, this is also a good multiferroic material at room temperature. In another study, it has also been used for electrocatalytic as well as photocatalytic hydrogen evolution process simultaneously. And it has been observed that the nanoparticles which were prepared by this reverse microemulsion method, and through for photocatalytic hydrogen evolution, these particles achieved a maximum production rate for a sacrificial agent. And similarly, we have researchers have observed very nice electrocatalytic properties also. For example, hydrogen evolution reaction were possible there in low onset potential of minus 0.115 volt and an over potential of minus 0.29 volts at minus 10 milliampere, and it also exhibits some built-in electric field that could give rise to some ferroelectric behavior in this sample. So our objective is to reduce its band gap so that it can work as a wastewater treatment photocatalyst in the visible radiation, and to provide more nucleation site to the materials by fabricating its nanocomposite with reduced graphene oxide. So first we prepared the nanomaterials, and the nanomaterials are the pure compound dysprosium chromate. Then the second one is with GD doping, 50% GD doping, and third compound is with yttrium doping. So all the samples were prepared by following Sol-Gel autocombustion method, in which the nitrates were taken and their stoichiometry ratio were taken in DI water, then citric acid and ethylene glycol was added, and they were stirred on a magnetic stirrer. Then drop-wise ammonia solution was added so that we could have the pH solution pH of the solution something around 10. And then there was a nice solution formation, which was again treated at 80 degrees centigrade for several hours, so that gel solution could be converted into a gel, which was dried at 120 degrees centigrade. And from the gel, we grind. It was a dry lump powder, and which was ground and again treated or annealed at 800 degrees centigrade for 2 to 3 hours. So this way we formed these nanomaterials. So basically, we have used these characterization techniques to characterize these materials: X-ray diffraction, field emission scanning electron microscopy, diffuse reflectance spectroscopy for the band gap measurement, and we have performed the photocatalytic measurements on these materials. So first, we discuss the result on gadolinium and ytterbium doped DYCrO3 compound. We intensely doped gadolinium because gadolinium is larger in size in comparison to dysprosium, whereas ytterbium is smaller in size with dysprosium. So we synthesize these samples using the solid state reaction method, and this diagram shows the single phase formation for these compounds. We performed the Ritwell refinement, and Ritwell refinement is good if this goodness of fitting parameter chi-square is very close to 1, and from here you can see. So these are the results of lattice parameter for the undoped compound, where we can see that the lattice volume of the pristine compound is 219 angstrom cube, whereas with GD doping the lattice volume increases, whereas with ytterbium doping the lattice volume decreases. And these are all the profile factors. We also calculated what is the strain present in these synthesized materials. We also performed the scanning electron micrographs of these synthesized samples, and then we, using the ImageJ software, we calculated what is the average grain size. So for this DGCO compound, the average grain size is something around 93 nanometer, whereas for this ytterbium doped compound, this grain size is 89 nanometer. Then, in order to have the idea of how the band gap changes when we dope gadolinium and ytterbium in this compound, we performed the diffuse reflectance spectroscopy on these materials, and reflectance data was collected as a function of incident light wavelength, and we convert then the reflectance data to the Kubelka-Monk function using this relation, and then we plotted the square times the Kubelka-Monk function times the incident energy square versus the incident energy square, and we get such type of graph where the extrapolation gives the value of band gap. So for ytterbium doped DYCO compound, the optical band gap is 2.61 electron volt, whereas for GD doped compound the band gap increases up to 3.39 electron volts. So therefore this material is suitable for visible light photocatalysis, whereas this material is suitable for UV light photocatalysis. Then we wanted to have a confirmation whether the synthesized materials are direct band in semiconductor or indirect band semiconductors. Direct band semiconductor photocatalysts are better for photocatalytic activity. Therefore, we confirmed through this fitting in which the multiplication of this Kubelka-Monk function with incident energy and h nu minus Eg are plotted, and this diagram, if the value of this P is close to 0.5, then it is a direct band semiconductor. If it is close to 2, then it is an indirect band semiconductor. So from the fitting, we obtained value close to 0.5. So it means that our synthesized materials are direct band semiconductor suitable for the photocatalytic applications. Then we perform the photocatalytic applications of these photocatalysis on this very important dye, which is known as the rhodamine B dye. And from the diagrams, you can see that as a function of temperature, as a function, so by the way, rhodamine dye also show absorption peak something around 553 nanometer, and you can see as we keep these photocatalysts containing dye solution under direct sunlight, so the absorbance decreases. It means dye concentration decreases here, and in 3 hours of exposure of sunlight to this material, we could degrade 84% of dye. Similarly, for this gadolinium dope compound, as I mentioned you, it has a large band gap of 3.31 electron volt. Therefore, it is more suitable for UV light, not for visible light. So therefore, it could degrade only 50% of rhodamine B dye. And then from these graphs, we calculated what is the rate constant. We fitted the data with first order kinematics, and we calculated the rate constant, which the value of rate constants are very, very higher in comparison to the pure compound. So we prepared another type of material, so also in which we doped manganese at the chromium site. We doped manganese at chromium site, and we prepared 20% manganese doped dysprosium rare earth chromite, and we also prepared 50% manganese doped DYCO compound, and in which we can see that DCMO 20% manganese doped compound could degrade 86.4% manganese, this rhodamine dye, whereas this 50% manganese doped compound could degrade 92% of rhodamine dye in 3 hours. We also doped holmium in this dysprosium chromite, and we prepared this sample and checked the samples for single phase formation through the XRD measurement and its Rittville refinement. The Rittville refined parameters, the lattice parameters are given in this tabular form, where we can see that the lattice parameter for the pristine compound, lattice volume for the pristine compound is 219 angstrom cube, whereas with the doping of holmium it decreases because the size of holmium is smaller than that of dysprosium compound, and we obtained several parameters. Then we calculated their crystallite size for the 2 doped compounds, and we confirmed if there is any impurity element also present in the compound. We confirmed it through EDAX. We could see only the in DYCO compound we could see only the peaks related to dysprosium, chromium, oxygen, and in holmium doped compound we could also see the peak related to holmium, and no other extra peaks were present there. We calculated the band gap of the 2 synthesized materials. So band gap for pure compound was 2.91 electron volt, whereas for 2.96 electron volt for pure compound DCO compound, and for holmium doped compound it was 2.91 electron volt. We calculated the band gap positions using some theoretical calculations, and from the diagrams you can see that if this is the valence, this is the conduction band age, this is the conduction band age, and it is the energy level for superoxide radical. So if the conduction band age is less negative in comparison to this superoxide energy level, then this superoxide radical will degrade the RHB dye. Similarly, hydroxyl ions energy level is this much. If the valence band position is more positive than this, then this oxide radical will also be used for the degradation of dye. So then we performed the photocatalytic measurement on these 2 synthesized materials, and we could see that for rhodamine dye, the pristine compound could degrade only 54% of the RHB dye in almost 4 hours, whereas DHCO compound could degrade 69% of dye in 4 hours. We calculated the rate constant also. So far I have discussed about the nanomaterials, and now I would like to discuss the photocatalytic performance on the nanocomposite. Why nanocomposite formation is required, and nanocomposite with a 2-dimensional material like reduced graphene oxide. Why reduced graphene oxide is important? It exhibits almost all the properties that is exhibited by graphene, and this reduced graphene oxide is also soluble in DI water. It has large surface area, and it has good affinity for the adsorption of organic molecules by pi-pi interaction. It acts as an acceptor and transporter of electrons, which enhances the photocatalytic activity of pollutants, degradation, and hydrogen evolution. This leads to more efficient charge separation and suppresses the recombination of electron hole pairs. Therefore, now research is going on to have the nanocomposites with 2D materials. So what we prepared, we prepared the nanocomposites for nanocomposite of this pure compound with reduced graphene oxide, and holmium doped DCO compound with reduced graphene oxide. The reduced graphene oxide was prepared by following the modified Hammer's method, and then the nanocomposites were prepared using this method that is shown here. So we performed the XRD analysis to check whether the composite formation has taken place or not. From the XRD diagram, you can see that there are all characteristic peaks related to DCO compound as well as DCO compound. Along with that, there are peaks related to reduced graphene oxide. So from this, we can see that there is formation of nanocomposites. So then from this, using the Williamson hole plot, we calculated the crystallite size for the holmium doped nanocomposite. It was around 49 nanometer, whereas for DCO compound, it was around 65 nanometer. We checked their surface morphology of the nanocomposites, and from the same image, you can see that there are grains related to DYCO or DHCO compound, and there are large sheets. Probably you cannot see here, but there are large sheets related to reduced graphene oxide also. So from the IDEX measurement, we confirmed that there are carbon present, there are elements related to DYCO compound, and then we calculated their band gap. So band gap significantly reduces in the nanocomposites. For DCO RGO compound, the band gap was 2.63 electron volt, whereas for the pristine compound, it was something around 2.91 electron volt. For holmium doped DCO compound and its nanocomposite with reduced graphene oxide, the band gap was 2.5 electron volt. And we performed the photocatalytic measurement on these to synthesize nanocomposites. From these diagrams, we can see that within a 3 hour, the DCO compound and its nanocomposite with reduced graphene oxide could degrade 87% of rhodamine dye, whereas in case of holmium doped DCO compound and its nanocomposite with RGO, we could degrade 96% of rhodamine dye in just 3 hours. We calculated the rate constant, and rate constant for these two reactions, photocatalytic reactions, were very high in comparison to the nanomaterials that we discussed previously. So these are the results that we obtained on these materials, on nanomaterials, and on their composites with reduced graphene oxide. So we could degrade 96% rhodamine B dye in just 3 hours. So this is the mechanism of photocatalytic degradation. You have the semiconductor, and light is incident on this material, then electrons are promoted to the conduction band, whereas hole remains in the valence band. So then these electrons are transferred to this reduced graphene oxide, which is a two-dimensional layer, because it acts as an acceptor or electron sink, and therefore in water, oxygen is present. These electrons will react with oxygen and they will form superoxide radicals, which is shown by this symbol, and this whole will be transferred and they will react with water on the reduced graphene oxide surface, which would convert water into the hydroxyl radicals. These superoxide radical and hydroxyl radical, they will react with the dye, and therefore it will degrade them. By color, you can see the degradation. This is for methylene blue dye, which is blue in color, and you can see how the color is changing. Rhodamine dye is pink in color, and therefore after several times of putting this dye containing solution in water, you can see how the color is fading. This means dye is getting degraded. So we have used these photocomposites not only for rhodamine dye. There is another important dye, that is methylene blue dye, and we have obtained important results. This is all I have discussed. So we have compared our results with already reported data, and we could see that we have obtained very important result, interesting results if you compare with the literature. 96% of rhodamine dye in just 180 minutes or 3 hours. We could degrade almost all rhodamine dye in just 3 hours. So these nanocomposites are not only important for photocatalytic activity, they are important for hydrogen generation also by water splitting. And it has been seen that it's nanocomposite with molybdenum disulfide, MOS2. MOS2, it produces it produces 393.2 micromole per gram per hour of hydrogen evolution reaction, which was higher than the pure compound as well as this titania compound, which is a typical photocatalytic material. So this material, this nanocomposite, has also shown significant hydrogen production through water splitting. It has also been used to degrade the antibiotics which are present in water, like results have been obtained on levofloxacin, and it has been shown that it could degrade with this compound 85% dysprosium chromite and 15% MOS2. The authors could degrade 84% of this LFX in 4 hours. So with this, I conclude my talk with the conclusion. We have used diffuse reflectance spectroscopy to measure the optical band gap of synthesized nanomaterials and nanocomposites, and we could observe decomposition of rhodamine dye up to 84% in case of ytterbium doped DYCO compound, whereas in case of gadolinium doped DYCO compound, the degradation was 54%. We observed structural, and we performed structural and morphological analysis, and that confirmed the successful formation of nanocomposites by the dispersion of reduced graphene oxide nanoseeds in these nanoparticles. The nanocomposites reduced their band gap from 2.96 to 2.63 and from 2.91 to 2.58, and we could observe enhancement of almost all the dye degradation in these nanocomposites. So with this, thank you very much.
Thank you, Dr. Neeraj, for such an informative talk. And the topic is very relevant to the sustainable. So, the audience, any questions, please?
Nice to meet you, sir.
Thank you.
My concern is about the secondary polymers because you are using rare earth metals like nitro.
Yes.
So what about this secondary polymer? The gadolinium you are using is reacted to react to water. So what about the second primary polymer you are taking out through photocatalysis? What about
Yes,
the secondary polymer you are using through this?
Yes. So these are like paramagnetic samples, solo magnetic samples also. With the help of a magnet, they can be taken out.
And these band gap are direct or indirect?
This is direct band material.
With such so much of doping and all that, is it possible to get such a direct band materials?
Yes, through analysis, I showed on one slide. We have confirmed that it is a direct band material.
Any further questions, audience? So thank you, sir, for coming in such fun and giving a very nice presentation here. So it's time to felicitate you.
स्लाइड चेंज तो Good morning everyone. I am Sanjay Kumar, working in DRDO on a project of growth of PMNPT single crystal. It has two steps. In first step, we synthesize PMNPT powder and in the second step, we grow single crystal from this powder. There are many issues in the synthesis of PMNPT powder. This is not easy task. So I will discuss here the issues and the solution for the synthesis of PMNPT powder. This is the overview of my talk. I will discuss what is the piezoelectricity and the introduction of PMNPT and the powder synthesis and the issues and challenges and solution. What is piezoelectricity? Piezoelectricity is a property of certain materials. When we apply any stress on them, then they generate electricity, as we all know, and the vice versa. This is a common material, barium titanate, which has the piezoelectricity. And this is the piezoelectric charge constant. It is the measure of electric charge generated on applying a per unit of force. Here D33. This 3 is generally represent the Z direction, and next D33 also represent the direction in which we measure the generated charge. Electromechanical coupling factor. It is the ratio of how much mechanical energy is converted in electrical energy. Curie temperature. It is the temperature above which the material has lose its ferroelectric property, and the dielectric loss. It measures how much electrical energy is wasted in the form of heat. This is the first generation of a piezoelectric material. It has the D33 around 2 picocoulomb per Newton. In the second generation, we have PJT, which has D33 around 300 to 600. In the third generation, we have PMNPT, which has the D33 around 1500 to 2000. And coupling coefficient around 95%, which is significantly large. Now we will discuss PMNPT. In the PMNPT, there are two compositions. First is PMN and second is PT. PMN is a relaxer ferroelectric which has high D33 but low TC, around -10 to -15. That is not useful for us. But PT has the TC around 450 degrees Celsius. So we combine both them and we get the TC around 150. That is usable for the device application. PMNPT powder synthesis, it has two steps. In the first step, we mix MgO with NVO25 to synthesize the Mn, and in the second step, synthesize Mn is mixed with Pb3O4 with TiO2, then the PMNPT is achieved. This is shown the Mn synthesis temperature plot. The Mn powder was synthesized or calcined at 1200 degrees Celsius for 15 hours. And the PMNPT, we calcined at 950 degrees Celsius for 4 hours. There are the major issues in the Mn synthesis is that when we react, the reaction with MgO with NVO25 is quite challenging because of there is a significant difference in the particle size of MgO and NVO25. If, as it is shown, when we choose 44 micron both of them, then the perovskite percent is quite low or pyrochlor phase is quite high, around 33.85%. In the second step, we reduce the particle size of MgO to 0.02 to 0.08 micron, and the second will be remain same, but the pyrochlor will be increased. In the third step, the particle size of MgO is reduced to 4 micron, and the NVO2 will remain same, but our issue is not resolved. In the final fourth step, both the particle size are reduced in the nano range, then the issues were resolved and we get the 100% perovskite phase. The XRD of each step is shown here. When the particle size of these are different and the perovskite phase is not achieved, the pyrochlor phase is present in this, then the PMNPT was synthesized or calcined with this Mn has many pyrochlor peaks as shown in the figure. But when we use the fourth step Mn and the synthesized PMNPT has no pyrochlor phase, it achieved all the perovskite phase. This is the PMNPT synthesis calcination temperature, and the XRDs of different temperatures are shown here. When the calcination temperature was quite low, then Mn synthesis was not completely achieved because the XRD shows unreacted NVO2. When we tries to resinter the same powder at 1200 degrees Celsius for 8 hours, but the issue was not resolved. Then we grind the powder and the calcination was retried, but the issues were not resolved. But then we compensate the remaining NVO2 with MgO, then the process was recalcined and the issues were resolved. This is in the fourth step. Here a major challenge in this step was when the calcination temperature is 850 degrees Celsius. Both the PMN and PT is not combined to form the PMNPT. This is shown in the black plot. But when we increase the temperature 900 degrees Celsius, the issue is quite reduced but not resolved. But when the temperature is increased to 950 degrees Celsius, then we got the pure PMNPT powder and the issue is resolved. That exactly match with the PMNPT JCPDS data. This is all. Thank you.
Why call it powder synthesis, ceramic powder synthesis? You are using 1 milli.
Yes, sir.
Why call it ceramic powder synthesis?
Yeah.
You are using 1 milli.
Sir, this is the powder synthesis. Ball milling is the process of what we used. Not the. Yes, sir. हाँ, तो powder synthesis is the same. This is the step. We also use motor pestle to achieve this. But sir, it is not possible to retrieve this because it is initially 2 phases, PMN and PT, but a third phase is also present, that is pyrochlor phase. So we are trying but not achieve the retrieve refinement for the 3 phases simultaneously. Sir, we want third phase to reduce, but it is not achievable because it is highly oxide. Lead is highly oxide, highly reactive. So this is the main issue in the synthesis of PMNPT, कि we can't reduce it 0%. so we can't achieve the ritual refinement with the third phase.
Thank you, Mr. Sani. So, the next oral presentation. Next oral presentation is of Miss Benazir Fatima. She is from Kishan PG College, Barrett, UP. Try to finish within 8 to 10 minutes.
Good morning, everyone. I am Benazir Fatima Yusufzai, a research scholar. Today I am going to present my work on Heusler alloys. Thank you. So, as you see the photo here, this is Friedrich Heusler. In 1903, Friedrich Heusler discovered something unusual alloy. There are three non-magnetic metals. Individually, copper, manganese, aluminium are non-magnetic metals. But when Heusler combined all them together, they started to they behaved like a ferromagnetic alloy, which is a strong metallic magnet. And you can see here in the down periodic table of Heusler compounds, X2YZ is a full Heusler and XYZ shows the Heusler compounds. So, origin of magnetism in Heusler alloys. How magnetism happen in Heusler alloys. So, in compounds, magnetism arises due to partially filled d orbitals. So, the half-filled electrons behave like a tiny magnets which went in the same direction of the magnetism and shows magnetism. Exchange interaction electrons leads to spin alignment. You can see here in the down, spin up and spin down half metallicity special case, in which if it happens, the electron shows the spin up, they behave like a metallic compounds, and if it's showing the spin down, it behaves like an insulating compound. So why Heusler? In the first picture, you can see the spin up and spin down shows the metal in the same way. The B is similar to the A, but it is in different phase. So it also shows the spin resolved metal, but it is different from the first one. If you can go to the C, ferromagnetic, one is showing the spin up and other is spin down. The most important actually is the D part. The half is showing the magnetic moment and half is showing the semiconductor. So this will actually work on the half Heusler compounds. This is used. And E is similar to the D, but it is compensated, as you can see that overlapping at here. It shows the half metallic but ferromagnetic. These are the examples of ferromagnetic Ni2MnSb, Mn2NiSb, and NiMnSb, CO2MnSi are half metallic ferromagnetic, and the other ones are. So, an overview about half Heusler and full Heusler. As we know, the Heusler compound are XYZ and shows FCC, and it has 4 lattices, but one is vacant. As you can see in the first structure, zinc blend and rock salts gives half Heusler structure, where you can see the vacancy of 1 atom site. So this is the basic structure of the half Heusler. If you go NiMnSb's actual structure, you can clearly find the difference. When you added the excess Ni in it, it becomes full X2YZ, which shows a full Heusler. In the right side of slide, you can see the graph of the half Heusler, half metallicity. density of states for NiMnSb. So these are the examples of some magnetic properties showing, like CO2 TiSi, it gives zero magnetic moments. Zt is the total magnetic moment of the compounds. CO2 TiSi. As you can see, we are changing the Ti with V and chromium, manganese. You can see how changing the 0 to 1 mu B and 2 mu B, like non-magnetic to weak ferromagnetic to strong ferromagnetic. Which means as you change the magnetic moment, as the increase of the magnetic moment, the magnetism increases, which is useful in half-Heusler alloys. These are the examples of half-Heusler alloys, TiNiSN. Here magnetic moment is 0 mu B, which is non-magnetic, and as we go further to the down, NiMnSb, the magnetic moment is 1 mu B, which is a strong ferromagnetism. Now we are moving to the Slater-Pauling rule. Slater-Pauling rule is used to find the total magnetic moment. How we are going to find the total magnetic moment? So for a half Heusler, we can use the formula Mt is equal to Nv minus 18 for Heusler, half Heusler, and for the full Heusler, we use two formulas. Normally, we use the first one on the above, Mt is equal to Nv minus 24, but in some special cases, we use the second formula when the atom size are more. For example, if we see the example of NiMnSb, half Heusler, the valence electron in nickel is 10, manganese 7, and Sb antimony 5. If we added all them together, we get the value of 22. And when we find when we put it in the magnetic moment formula, it is 22 minus 18, which is equal to 4 mu B, which is a very strong ferromagnetic material moment. Now this is my simulated XRD data of Mn2 NiGa CO, Ga 0.5, cobalt 0.5. As we actually know that we have normally two compounds are D transition elements and one is P type. But for I have changed that. With half I take gallium, which is a p-type element, and half I take as cobalt, which is a magnetic element. So you can see the ratio of the is 0.24. We are going to further compare them with the other slides. Now you can see the second simulated XRD data of Mn2 and ICO, where the value of the ratio is changed to 3.88. As you see in the before, it is 0.24, but in here it is 3.88. Why it is changing? We have used here the prototype structure of Cu2MnAl, which is a basic structure used by Friedrich Heusler. I am trying to, okay, I'll do the little fast. Okay, so next slide is about Mn2, we change it and the ratio becomes 0.48. As ma'am is saying, I'm doing a little bit more. And then the ratio is 0.74 as we change Mn2 and IgA, which is the actual one. So here is the co-concentration variation ratio. You can see how if you put the value of X0 here, so cobalt, you can see the concentration value of cobalt. Now this is the experiment data of co-substituted IgA site in Mn2 and IgA, where simply you can say that if you add the cobalt in it, in place of gallium, it becomes more magnetic. And if you add the gallium in the place of nickel, as you can see the blue line here with a blue dot, so it is same, because normally we have two D-transition element and one is P-type, but we are changing the P-type element with a D-type, which is already magnetic, so it is normally going to be more magnetic. So in conclusion, this is it's all applicable in spintonic devices. Thank you.
Any questions?
On Vesta software, I simulated the data and then compared this with the result of other researchers. As I just started it is my beginning of research. So I have just, I'm going to do the experiment actually, but now because I have little hurried to come here, so I compared my simulated data with the different researchers. Yes, sir. Yes, sir. Is a metallic, no, sorry, sir. Sir, can you, yes, sir. Yes, sir. Sir, can I use a water? My mouth is drying. Braces की वजह से. That is not. Yes, sir. What are you asking? Sir, can you speak little bit louder?
You have eminent 2 NIGA.
Yes, sir.
Okay, GA MN and NIE are the 3D transition metal.
MN and NIR?
3D transition metal element.
Yes, sir.
GA is an stable element.
Yes, sir.
You are substituting GA side with a 3D element.
Yes, sir.
Do you think that one is a real substitute?
Sir, we need why Heusler alloys to apply in, Curie temperature. Sir, I meant that if we change the P-type element with that element, cobalt, it became more magnetic. Normally, Heusler alloys have both to do our T-transition element and P-type, and we are doping the that one is with them. Thank you.
With this, now we will take a short break for 20 minutes for tea, and the tea will be served at Samarth Guru Ramdas Auditorium.
morning to all of you. I am Dr. Nancy, working as a postdoctoral fellow under Dr. Nirban Das in Amity University, Gurugram. So I'm going to present on the topic investigation of titanium dioxide nanoparticle integration on polypropylene membranes for enhanced performance. So this is the overview of my presentation. First I'll introduce about the polypropylene membranes, their importance, their introduction and its limitations. And then I'll briefly introduce about the research objective which we have done so far in this project, and then the synthesis route which we have followed to perform this integration. Now and after that we will focus on the results which we have done using IC-SFAM, XRD analysis, FTI analysis and XPS analysis. And then we have performed wettability results using water contact angle, and then further on the conclusions. Now what is a polypropylene membrane? Polypropylene membrane is a proper polymer that is basically important because of its excellent thermal stability, chemical resistance, mechanical strength and affordability. It is distinguished as a highly versatile thermoplastic polymer and due to its ease of processing. Now moving on to the application part, it has a variety of applications including biomedical as well as non-biomedical applications. In case of biomedical application, it can be used for hernia repair mesh, breast reconstruction support, and in non-biomedical case, it can be used for water as well as air filtration. So, after being a very versatile material, it also has some limitations. It shows high manufacturing and preparation time it takes, and the sensitivity to moisture contact. It can easily get affected when contact with some water or moisture. During sunlight exposure, it can also be degraded. It has poor bonding. And it is hydrophobic in nature. Hydrophobic means it has less wettability. It does not get easily wet. Next, the research. So, like focusing on the limitation, that is poor bonding and the less adhesion. So, we have considered on this research objective to activate the polypropylene membranes. So, polypropylene membrane being hydrophobic. So, what we have done in this work. First, we have done the polypropylene done the aminated ammonia plasma treatment, or we can call amination of the polypropylene membrane. So that can be done just to improve the adhesion, enhanced hydrophilicity, increased surface reactivity for functional coating, enhanced chemical compatibility and reactivity, and to facilitate the surface grafting. And after subsequent amination, we deposit the aminated membrane on titania on the aminated membranes. This is the synthesis route which we have followed. First, we have done the preparation of coating solution, where we took the beaker and titanium tetraisopropoxide mixed with ethanol, and then stir for some 1 hour 10 minutes, and the membrane is put in the that solution and stirring for 1 hour 2 minutes, and then after that we remove the membrane and just air dry with room temperature, and then after some analysis has been done to confirm the integration of titania on the membranes. So these are the also the notations we have used for the subsequent slides. Yeah, these are the results in discussion. First, I have chosen the morphological curves. From the morphological results, we can clearly see that AMT0 shows the bare polypropylene, AMT2 shows the aminated one, and E2T2 is the membrane that is titania coated on aminated one. So, from the results, it can be easily seen that the porosity is increasing for aminated membrane. However, for titania coated membranes, we can easily see the partial pore coverage on the hierarchical microstructure surface. Or we can see if we compare the untreated polypropylene membrane with the aminated polypropylene membrane, we can see the pores size are increasing, which clearly indicates the hydrophilicity is increasing. or we can say that it provides the active sites for reactivity with other materials. Oh, sorry. Yeah, these are the XRD results. We have performed for the structural conformation. So we have performed the XRD measurements for untreated as well as aminated polypropylene membranes. The results indicates the characteristic polypropylene peaks at 14 degree, 16.9, 18.5 and 21.8 to theta values, which confirms the polypropylene structure, whereas for aminated one the same peaks has been observed, but with the shifted corresponds to the increase in the crystal size and ordered structure. So the further with the titania coated on untreated as well as the aminated membranes, we have done the XRD analysis. We can see the extra peak that is corresponding to titania rutile phase at around 42.7, that confirms the presence of titania, or we can say the incorporation of titania is successful. So these are the in order to check the chemical environment, we performed the FTR results. For untreated, if we see the left figure that shows the untreated polypropylene and aminated polypropylene membranes, we have observed the aliphatic CH structure for corresponding to polypropylene, that is the characteristics band for correspond at 2951 corresponds to CH and antisymmetry CH3 stretching. And for 1454 it corresponds to CH that is symmetric CH2 banding. For 973.8 corresponds to carbon-carbon stretch, that is carbon-carbon stretching. So for if we focus for the plasma treated polypropylene, we can see there is a broad band here at 3300 and here at 1670, around 1670. That corresponds to the amination. That the band corresponding to 3300 corresponds to NH stretching, and that 1670 that corresponds to CN stretching. That confirms the presence of amino groups on the polypropylene membranes. That shows the successful amination of the membranes. Now focusing on the titania coated on aminated one, we have seen the broad band corresponding to titania incorporation at lower wave number around 500 to 700 and higher wave number around 3400. So these at 3400 it corresponds to the hydroxyl group of bands, and that at lower wave number it corresponds to the titania oxygen stretching vibrations. Yeah, these are the also to for better understanding or for the chemical composition analysis, we have performed the XPS measurements, where we have where we can see that the XPS surface spectra corresponding to untreated polypropylene and the aminated polypropylene. For untreated propylene, we can easily see the carbon 1s peaks at 285 and only oxygen 1s peak. That confirms the presence of only polypropylene. So if we focus on the aminated one, we can see the clear peak corresponding to N1s. That is at 399 electron volt. And the enhanced O1s peak, that corresponds to the proper crystallization of amination. This confirms that presence of N1s peak in the aminated membrane confirms the successful high degree of amination. Further, the titania coated on type 2, or we can say on the aminated membrane, the results shows the presence of Ti2p. So we further deconvoluted the results using origin, where we have we can see the titania 2p 3/2 core at 458 and 2p 1/2 at 463.9 with the spin orbit splitting of 5.7 electron volt confirms the presence of titania is in stoichiometry. Ti4 plus is in stoichiometry titania oxide structure on the membrane. So further, the water contact angle. The water contact angle is the angle that made at the interface between the water, air and the solid surface. That defines the wettability. Means if any membrane has a lower value of water contact angle, means it is more hydrophilic. And if it is having the higher value of water contact angle, it shows the more hydrophobic nature. So these are the results which we have done at Jamia. So we have measured at the Jamia. So these are the result of the membranes. So we can see for untreated polypropylene membrane being very hydrophobic in nature, we have observed the water contact angle at 99 degree, or after amination a drastic decrease in the water contact angle has been observed, that is 45. So this clearly indicates that the successful amination, that means the active sites has been created after amination. Okay. Yeah. So further, we have performed the water contact angle of the material, that is the titania coated on the untreated polypropylene membrane only. So for that we have observed the superior hydrophilicity. We can see the change of from 99 to 42 degree. So that drastic change with titania coating, only after titania coating we have observed for the wettability results. So that shows the superior hydrophilic in nature for the titania coated on polypropylene membranes, which benefits for oil water separation and water filtration, air filtration and anti-fouling applications. So these are the conclusions. So we have done the IC-SFAM results, which shows that the untreated polypropylene membranes are standard porous in nature. With amination, we have seen the enhanced porosity, and with titania coating, hierarchical microstructure as well as decrease in the porous nature has been observed, and little coverage of that porosity. For the surface chemistry, we performed the FTR XPS, which shows the aliphatic CH banding, and for aminated membranes, we have observed nitrogen integration. We have confirmed that using various measurements, and for titania integrated membranes, we have observed the corresponding vibrations of titania oxygen and titania hydroxyl group confirms the presence of Ti4 plus in stoichiometry titania. Further, the functional wettability has been measured using water contact angle, where we have seen the interesting results from 98 degree to 46 degree for aminated one, and for titania coated we have observed the 42 degree, that shows the superior hydrophilicity. So the strategic integration of ammonia plasma activation and titanium nanoparticle deposition successfully engineered the surface of polypropylene, eliminating its fundamental limitations while preserving its structural integrity. Thank you. Thank you. Sir, we have not performed the plasma treatment. Actually, that is done in the US only. That where the project we there AMT Industries. US. They perform the plasma activation, and then they provide the membranes to us, that we do the metal oxide coating on that. Yeah, we have the ready membranes, polypropylene membranes, as well as the aminated one. We perform the metal oxide coating on that. Anyone else? Okay, thank you so much.
Tatir Fatma Jafri from Mahapateshwar University.
Okay, good morning everyone. This is Tatir Fatma Jafri from Kisan PG College, Bahraich, UP. This time I have a headache, that's why I'm nervous. No, thanks. It's migraine headache है, जल्दी नहीं जाएगा.
इसे रहने दे अभी.
What sir said? I didn't understand sir.
केवल रिजल्ट दिखा सकते हो क्योंकि इंट्रोडक्शन तो आपके फ्रेंड ने दिखा दिया है.
And Ayush, she has already presented introduction, so it will be easy for you.
रिजल्ट आप सिर्फ रिजल्ट दिखा सकते हो. सही बोल रहे हैं. थोड़ी देर बाद.
Okay sir, I'll try. Okay sir. Can I have some water, please? No, it's not in the migraine headache for that. That's why. Yes, sir. ये बार-बार ये कहने से मैं इसलिए. Sir, I'll explain. Yes, sir. Yes, sir. Sir, theoretical magnetic moment explained. total magnetic moment, to find total magnetic moment. Yes. Sir, like, I don't know, vanish everything. About 2 or 3 months. Sir, in this graph we studied and similarity XRD. Stimulated XRD. Yes. So magnet. Okay, sir, I'll explain. This slide compares the magnetic properties of CO2 FeSi and CO2 MnSi. By comparing them, we can see how changing elements affects magnetism. So red line shows high magnetic moment. Red line. Sir, it is perpendicular to that. Everything is vanished in the magnet. I'm sorry. Thank you, sir.
Now next, moving ahead, we are having Dr. Omveer Singh. Is he present here? I think he has not yet. So can you go ahead, Dr. Pushpa? Okay, ma'am. You can go.
Okay, good afternoon everyone. This is Professor Pushpa Bindal from Kalindi College, University of Delhi, and I am here to present our work on characterization of step index multimode optical fibers. So the outline of the talk will be first talking about construction and working principle of optical fibers. Then we'll understand how to go about the modal analysis of step index fiber and work out the propagation characteristics of a step index fiber. And that means evaluation of normalized propagation constant, modal field and spot sizes. So the first question that comes to our mind is, why are we interested in optical fibers? Optical fibers, they offer a high bandwidth over large distance. A very less attenuation has been reached, almost theoretically, achievable, theoretical limit achievable low power loss, and that allows for long transmission distances. Since the fiber is a dielectric medium, it does not present a spark hazard, and it is immune to electromagnetic interference, and therefore the data transmission is very secure. So the applications of optical fibers are immense. We have many uses, many applications in medical industry. We can talk about endoscopy, we can talk about pinpointed treatment of cancerous cells, then data storing equipment, telecommunication we already know, then in oil and gas industries also, that also is very popular nowadays. The optical fibers are being used for decorative preparation of decorative materials, for local transports, in aerospace and avionic industry also, in military also for secure data transmission and network. So what is an optical fiber? Optical fiber is basically a very thin strands made of plastic. You can see the cross section. It has a high index core medium, mostly it is silica, surrounded by a slightly lower index cladding medium, and for support and protection we do give a plastic coating also. So the refractive index of the optical fiber, as you can see, we can say if core has a refractive index N1 and cladding has a N2, then N2 has to be slightly less than N1 because the guidance takes place mainly through total internal reflection. So the categorization of optical fibers are done in many ways. One of them is that you can talk about single mode and multi-mode fibers. Single mode has a very small core dia, typically of the range of 5 to 10 microns, and in multi-mode the core dia is somewhere, it goes around 50 to 70 microns, and if the core, if the refractive index is a constant throughout the core, then you call it a step index. Otherwise you can also have graded index as the requirement may be. Now to understand the modal analysis, to talk about the characterization, we need to solve the wave equation for the cylindrical system that a fiber represents. So typically the modal field will have a radial dependence and it will have an azimuthal dependence, and you will have propagation constant coming into picture as it propagates along the length of the fiber. So if you substitute the field in the wave equation correspondingly, you will end up with this equation that you can see here. Here K0 is the free space wave number and beta represents the propagation constant. Now the solutions are typically, it has a radial dependence, as I said it has an azimuthal dependence, and it represents the propagation also. We define terms like U and V which involve N1 and N2, that means the two dielectric media, and the propagation constant. When you substitute these fields in the wave equation, then you obtain these two equations for the core region and the cladding region. The solutions for step index fibers are given by these expressions, and if you add U and V, you arrive at a standard parameter called normalized wave parameter, defined as 2 pi by lambda naught under root n1 square minus n2 square multiplied by the core radius. Now in order to define the propagation characteristics universally, it is better to define a normalized propagation constant which is called B, and the definition of B is again in terms of beta, K0, N1, N2, and for guided modes you must have beta by K0 between the two refractive indices, and beta by K0 is also known as effective index of the optical fiber. Now when you use the boundary condition which are posed by the interface, that means the boundary between the core and the cladding, then the following two eigenvalue equations, transcendental equations are you obtain. The L is equal to 0 represents the fundamental mode of the optical fiber. This is supported by all kinds of fibers, whether it is single mode or it is multi-mode, and L greater than equal to 1, that represents the transcendental eigenvalue equation for higher order modes. One of the characterizing parameters is Peterman-2 spot size. And once again, this is defined in terms of the modal field and the variation of the modal field, how it is changing within the core and in the cladding region. And this is basically a representation of how fast the modal field decays inside the core. And when you substitute this for the step index, you arrive at the expression which is shown below this. Now here are some results. So if you plot the transcendental equation, both sides, left side, right side, you arrive at the solution for B, and this is the basically curve for the fundamental mode. Here we have used the, after obtaining the solution, which was 0.41610, we plotted the modal field of the fundamental mode, that is known as LP01 mode linear. You can see the variation in the core and the cladding region. Now we also varied the value of V, that you can do by either changing the refractive indices or changing the core dia or even the wavelength, but V represents kind of an overall effect. And as you increase the V, the modal field is bound to become more and more confined within the core, and therefore the value of the propagation constant is bound to increase with V. And if modal field is more confined, obviously the spot size will reduce. So we have also plotted the variation of the Peterman spot size versus V. It decreases. And here again, this is another plot which here we have basically plotted the same field, same fiber, but different values of V. So if you plot it for different values of V, then as you when the value of V is less, then the field leaks out to the cladding. So there is more loss, and it is possible to even you can lose the signal. But if you increase the value of V, then the field becomes confined. It is a better propagating field. Now we go to the higher order modes. First higher mode, this is the first antisymmetric mode supported by the fiber. This is known as LP11 mode. As you can see, it is an antisymmetric mode. At the center of the core, you get a zero field, and then you have a peak, and then finally again in the cladding it is bound to decrease because it is representing an evanescent field. This is the variation of spot size of LP11 mode. With V, again as V increases, the field becomes more confined, and therefore there is bound to be a reduction in the value of spot size. This is the next higher order mode, LP21 mode. This is the next antisymmetric mode supported by the fiber, and this is the modal field of that. This is the spot size variation of this mode with respect to V. Here we have put them together. We have shown all the modes in one graph, and basically they show how the modes are, modal fields are varying within the core and the cladding region for, different modes, fundamental, LP11, LP21, and you can actually talk about more modes. This is basically a 3D plot for LP01 and higher order mode, and this is the corresponding contour plot for various modes supported by the fiber. So here I summarize. We have talked about the importance of optical fibers, we have talked about the modal analysis, and we have learned how to go about the evaluation of propagation characteristics of the step index fiber. Thank you very much.
When you talk about the step index,
Sir, step index means that within the core the refractive index is 1, constant.
Yes.
And cladding will always have only one single refractive index, slightly less than that. But cladding in core, depending on what application you have in mind, it is possible to design to cater to the different refractive index profiles. So here I have only presented the results for step index, but it is possible to modulate that for different applications. Cladding core is more, the refractive index is more, and the cladding the slightly different, then only the total internal refraction can occur. Okay, we are interested in guiding the light through the fiber. So that can happen only when the the light is total internally reflected at both the interfaces. है ना? We launch it somehow. I mean, you have to, of course, cater to all the requirements. But once the light is launched, then it suffers total internal reflection like this. And the light goes undistorted, in shape, with a certain velocity throughout the fiber, and it travels thousands of kilometers like that. That is how the internet has come into picture. Internet, optical fibers have played a very immense role in the ultra fast internet that we are using today.
In one of the slides, you talk about spot size.
Spot size is basically a parameter. You see, depending on what the refractive index difference is, your modal field can vary. Okay, we are interested in less loss. We are interested in larger propagation distances because you don't want to spend so much of money. Because for every repeater that you install, after every few kilometers involves lot of work, lot of money. So we would like to work towards that goal where we can minimize the losses, where we can minimize the dispersion. You see, as the mode propagates, it is bound to disperse. It is bound to disperse, right? Particularly the multimode fibers, intramodal dispersion is also there. In single mode, there will be no intramodal, but still you will have material dispersion. You will still have waveguide dispersion. So the thing is that, but single mode is very expensive, very expensive. So this is used for, over the countries, the cables that are laid below the sea, at the sea level. Okay, but LAN, local area networks, there we are using multimode fibers. Spot size is a parameter. If field is varying like this, then basically I gave a definition, no? Integral psi square r dr divided by d psi by dr. It will have a unit of microns. Definitely, it will have a unit of micron.
Thank you.
Thank you.
Continuing this session further, we are having Mr. Pavan Kumar from CCS Meerut campus. You can go ahead. In this audience, Karan Singh. No.
Good afternoon, Chairperson, respected judges, all the faculty members and all the participants present here. Myself is Pawan Kumar, Research Scholar, Department of Physics, Chaudhry Charan Singh University, Meerut. Today I am going to present my presentation on the topic PT decorated 2D MOSC2 nanostructured thin film sensor fabricated via magneton sputtering for highly sensitive hydrogen detection. This work has been carried out from the supervised by Professor Anuj Kumar. As we know that hydrogen is a very clean energy carrier, but from its properties it is the very explosive in nature and very high flammability. So the detection of hydrogen is very crucial for the environmental safety as well as the industrial purpose. So first we will start the introduction part. So today we have demanded the development of sensing device which have the following qualities of the sensing: good qualities, cost effective, low power and operating at room temperature. But environmental have present that very noxious gases, inflammable gases, several VOCs. So real-time monitoring of these type of gases for the safety purpose is very important. So then today's demand is very for our sensor is highly sensitive sensor, selective, cost effective, low power consumption, simple operation and stability. So these are the key objectives of my research work as follows: development of 2D TMDs, MOSC2 and WSC2 sensors by physical vapor deposition as well as chemical vapor deposition, and optimize the various parameters such as deposition temperature, power, sputtering pressure, gas flow rate, etc., and then characterize them, and we will find all the sensing properties of the developed material. This is the methodology part of for sample preparation, and we have two deposition techniques: physical vapor deposition and chemical vapor deposition. So in my case I have worked on physical vapor deposition, in which we have done sputtering by DC sputtering and synthesized very safely. This is the sputtering technique mechanism. This is the sputtering chamber. The argon ion is inserted in the chamber, and argon ion strike on the target material, and atom is ejected and deposit on the thin film. This is the thin film growth of our sample. This is the sputtering chamber which is present in our department. Sputtering technique, these are the optimization parameter of this sample. Before optimizing these parameter, I have deposited 20 to 25 sample for different pressure, temperature and distance from target to substrate, and after that we have optimized this parameter for our sample. Characterization of 2D TMD nanostructured thin film. So these are the XRD of the preferential growth along the 006 axis of MOSC2, and after decorated the PT on MOSC2, so there is no impurity peaks is observed. That's why the confirm the crystallinity and phase of the MOSC2 oblique PT MOSC2 along the 006 plane at 41.58 degree. This is the FE-SAM morphology of pure MOSC2 and PT MOSC2. So in this figure clearly seen that the surface area of this pure MEH2 is small. After PT decorated on the sample, the surface area has been increased. That's why the sensing performance of the sensor also has been increased. This is the elemental mapping of ADS analysis, in which PT or selenide MO is uniformly distributed over all the sample. This slide shows the hydrophobic properties of the sensor. Pure MOSE2 is have the CA contact angle 97.4 degree, but after we decorated the PT on the MOSE2, the contact angle have been increased 103.63 degree, the 6 degree. That's why this is the very hydrophobic properties in nature. This is the device fabrication, electrode surfology, and this is the morphological view of device surface. This is the sensing setup in CSIR NPL Delhi, which I have worked, and here we put the sample and we enter the different gases into the chamber and measure the resistance of the film, and then we plot the IV graph and we get the result of this film. This is the gas sensing properties. So here we clearly shows that the MOSE2 response of these gases is very low, but after decorated PT the sensing response has been increased, which is shown in clearly. And this is the film sensor, and this is the concentration of 2 to 10 ppm in dry air. Cyclability test of proposed sensor to 10 ppm hydrogen at room temperature up to 6 cycle, and other results I am working on this sample. Conclusion: in the present work, bare MOSE2 and PT decorated MOSE2 nanocoral structure were directly synthesized on the porous silicon surface via DC splitting technique, and we have achieved the gas response in 46% to 10 ppm in dry air. But in this sensor we have this is the at room temperature, not to high 100 degree or 200 degree temperature. So that's why it is very important for future generation.
Thank you, Mr.
These are the references. Thanks to you.
Deposit this platinum MOS2 as a barrier.
No sir, this is the MOSE2 is single layer for 30-minute deposition, and after that for the sometimes we decorated the PT on the layer. Only on surface.
How is thickness of the
Thickness
thickness of the platinum?
300 nanometers sir. PT. Sir, this is unmeasurable because this is the spillover effect on the surface. That's why. What sir?
Platinum, how did you deposit? Using spotting?
DC spitting sir.
MOS2 is not deposit of the DC.
Sir, we have one chamber in which we have set 2 guns. I am showing that. One gun is sir MOSE2 and other is PT target. So first we deposit spitting 6 minutes for deposition time for MOSE2, and after PT decorated sir.
Here we are using substrate with the porous silicon.
Yes sir.
So is there any special requirement to use porous silicon or normal silicon?
Sir, normal silicon have no active sites for the absorption the gases, but in porous silicon we have the more and more active sites. That's why the more and more target gas is interact with the surface and give the better result for the sensing performance.
If I understood correctly, you have substrate. On the substrate you have MOS.
Yes sir.
On top of MOS2 you have platinum. Then how we are using the porous behavior of the substrate?
Sir, actually porous silicon have more and more porosity. That's why the growth of MOSE2 is also in porosity, a preferential layer. That's why porous surface area is more than the normal surface area. So more and more gas interact with this to give them better result for sensing performance, sir. Thank you, sir. Thank you all.
We are closing this session here as some of the participants has not come. So now the lunch timing is 1 o'clock. So we are meeting at 2 p.m. for session 5.
Hello, 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 hello. हेलो 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 ठीक है ओके
Good afternoon. I hope the lunch break was refreshing. We now resume the conference with session 5. May I kindly request our session chairperson, Dr. Ajit Kumar Patra, to please chair the session further.
Okay, welcome back to the post-lunch session. So welcome back to the post-lunch sessions of the second day of the conference. And we have 3 talks. The first invited talk will be given by Dr. Nazmul Afi, our old colleague of mine. And he is going to speak on the role of
Good afternoon, everyone. So I am Najmul Arfin. I'm working at Center for Interdisciplinary Research in Basic Sciences. And the topic of my talk will be role of Coacervates as a delivery system of drugs towards cancer cells. As the title suggests, it deals with Coacervates. I think as a physicist, most of the people are unfamiliar of the topic. And in cancer cells, obviously it's looked like a biology topic. So initially I was also afraid of, as a physicist, I was also afraid of to get into these kind of fields. But this is the era of interdisciplinary and we have to do it. And I think physicists can handle these kind of systems very fine. So if the students are sitting over here, one or two students, whoever is sitting over here, so if they are from physics background, if they are doing masters or graduation, they can take it that apart from several other subjects of physics like thin films, nanomaterials, crystal growth, multiferroics, supercapacitor, nonlinear dynamics and laser technology, there are interdisciplinary fields which most of the physicists we are unaware of. Like as a student, I was unaware of that some kind of interdisciplinary field we can switch after doing BSc and MSc. So what are those kind of fields which, because this is an era of interdisciplinary and there is a huge opportunity to switch over to those fields to explore many research problems. So what are those research problems? These are typical research problems related to biophysics. Like we have biochemistry, we have biotechnology, we have microbiology, but hardly, I don't know, mostly physicists don't get into these kind of stuff in general. But if some are at a student level, UG or PG, trying to explore this stuff, there are various fields like biomechanics, biophotonics, cellular molecular biology, cellular molecular biophysics, neurobiophysics, membrane biophysics, system and computational biophysics, and soft matter physics. So this is an example of biomechanics. So this is a mantis shrimp. It's basically found in sea. It's a palm-length kind of animal. But the biomechanics lies in the punching speed of this mantis shrimp. The boxing gloves create such an immense power that it can break the shell of a crab. So how these animals generate such huge amount of power or force, if those kind of studies someone wants to pursue, they can go to biomechanics. It is a kind of biomimetics field also. You can relate it to biomimetics. Now biophotonics. So where you can merge photonics with biological system and you can map cells and tissue by bioimaging, and also helps in seeing how the structure changes by using this biophotonics. Cellular and molecular biology, the folding, unfolding of protein, which regulates most of the biological functions, can be understood through cell and molecular biophysics. And these all has to do with the physical stuff only. The only part is that basically we are having a biological system, that's it. Everything is physics. Then neurobiophysics, so you put two electrodes in the mice and then you learn how the signal or waveform changes. Then my membrane biophysics, we know we have cells and we have membranes outside that cell, which is that membrane has a fatty layer. How things transport through that, means how the glucose goes through that, how proteins binds to it, how the ions goes inside the cell. That can be studied through this membrane biophysics. Computational and system biology. If you can write some equations and model the problem, biological system, you are basically doing system and computational biology. And soft matter physics, that is basically the point we'll be talking of. So soft matter physics, it's basically condensed matter physics, soft condensed matter physics. And it contains actually deals with polymers, colloids, gels, foams, biomaterials, liquid crystals. But my topic is Coacervate. In particular, we will be talking about Coacervates. So the first and foremost question is, what is Coacervate? What do you define Coacervate? So if you have, say, we have studied phase transition, ferro to para, para to ferro, that is phase transition. This is also kind of phase transition. So if you have two polymers homogeneously mixed in water, and with some condition the phase gets separated out such that the lower part is actually a liquid part and upper part is actually a liquid part. Both are liquid. The only difference is the lower part is a dense polymer phase, but it behaves like a liquid. It has viscoelastic properties like water. It has interfacial tension. It has a coalescence property like water. So this Coacervate phase is basically has tendency of that like that of water, but of fluid basically, but it is rich in polymer phase. And this liquid-liquid phase separated part is basically called Coacervate, which is formed by the interaction between oppositely charged polymers. These polymers could be anything, any polymers, biological polymers, synthetic polymers, colloids, anything. So the electrostatic interaction is not the only interaction we will be dealing with to get Coacervate. So if you have a single polymer and you play with the temperature, pH, ionic strength, constant concentration and solvent of the solvent, you get a Coacervate phase separated part of polymer, which is called simple Coacervate. Now if you have two oppositely charged polymer, is a case B, which binds through electrostatic interaction, and then you tune pH, ionic strength, temperature, then we call it as a complex Coacervate. That basically we will be dealing with. The other Coacervates are this multi-phase Coacervate, where you have different kinds of two or more kind of polymers, and they have different, like they do have phase separation, but they have different layers. And the last one is this is also this is also a Coacervate, but has a different structure. It can form when you have a charged polymer with some neutral element, and other can have a charged polymer with large neutral element. And if these combines, they can form a micelles or worm-like structure. These are also kind of Coacervates. So basically, the interaction of polymers or playing around with the temperature, solvent, pH, ionic strength can give a liquid-liquid phase separation system, and basically we get Coacervates. So these theories of Coacervation are very old. Fleury-Huggins have studied this phenomena of Coacervation on 2D lattice model, and they have taken into account this chi, the second equation, Fleury-Huggins model, the chi, which basically takes care of the phi is basically the volume fraction of the polymer, and chi is basically the interaction parameter between solid-solid, solvent-solvent, and solid-solvent. Then there is another interaction, there is another theory, Woon-Overbeek theory, which deals about the complex Coacervate basically, which talks about the interaction between a positive charge and negative charge and how these interactions takes place to get a phase separation. And it takes account of the electrostatic interaction. That part is basically mentioned over here, is sigma phi to the power 3 by 2. This electrostatic part is here. Now this is Ginsburg-Landau model. This also talks about the phase separation part. Here it talks about the gradient of concentration change at the critical point. So these are the basic theories that discuss with the Coacervation. So we have already studied so much for phase separation in physics. So why, and obviously the theoreticians are taking care of these kind of theories. So why, as an example, 50% of the physicists are experimentalists in theory and 50% are experimentalists. So why, as an experimentalist, I bother about these kind of theories? So to understand this, we should go back to the evolution of this coacervate. Like the universe, the evolution of the universe was not understood properly, same as the origin of the cells. So in 1911, this Tyback actually so in 1900, where it is? So in 1900, Tyback actually saw the phase separation between two polymers, that is gum arabic and gelatin, and it said there is some kind of a phase separation. But in 1924, I.A. Optical, in the book Origin of Life, he suggested that this phase separation is basically the reason for the origin of life, and from there the things started. And people have said that there could be different types of coacervation taking place, and that can mimic a cell, and that's how life begins. But you see, in 2021, there is a paper which clearly says that the droplets of mixing link between chemical and biological origin of life. So basically, these droplets are basically the coacervates, are basically the missing link between biology and the chemistry to form a cell. So still people are wondering whether how coacervates are playing a role in the origin of life. But that is not it. The evolution is not important. If we see the application of these coacervates, we see these are few examples, but you see the papers are of, like, this is a paper of Nature published in 2025 which mimics a cell. This is a coacervate which mimics a cell and published in 2025. There is a Nature Chemistry in 2025 which suggests that delivery of drugs can take place, because as already discussed that coacervate behaves like a cell, mimics like a cell. There is again a paper of 2015 where the hard beak of this, there is a hard beak of squid which is formed because of the coacervation process. Otherwise this hard beak cannot be formed. This is a liquid-liquid phase separation, drives the cellular function and dysfunction in cancer. That is again, and also it's in bioadhesive. So if you have a ship which gets corroded because of the interaction of microorganisms in the sea, that is because of the macro adhesion of those microorganisms with the ship. So those kind of studies also occurred because of the coacervates, because some coacervation is taking place. And all these papers suggest that coacervates has a huge impact and role in daily biomimetic systems. If I concentrate towards health and disease, then we can see that coacervates is basically responsible in DNA assembly. There is a DNA assembly and mitosis, singular transduction, cellular compartmentization, nuclear activity, gene expression. These all are related with the coacervation process. See, these are the papers which suggest that downstream signaling in the T cells is responsible. LLPS improves down signaling in the T cell system. So T cells, the activation of T cells depends on the coacervation process. Again, epigenetic control. So this is LLPS defines how the protein behaves and how the external factors works in a body. The self-aggregation process of, again, protein helps in the stress granule formed in the body. These are the few points where we can see that coacervation plays an important role in maintaining a good health. But if you have some disruption in the coacervation process, what will happen? There, LLPS in the protein encourages tumor growth and metastasis in breast cancer. So if you have some kind of uneven coacervation, unregulated coacervation, that gives cancers. A replication will alter. The LLPS in tau protein leads to Alzheimer's. So it's not just one thing. From very biomimetics to human health and disease, coacervation is everywhere, and we were unaware of that. So the point is, if coacervation mimics cells and if it has a major biological function in human health, and if we make Coacervate with biocompatible materials, can we use it as a drug carrier towards cancer cells? And how efficient that drug carrier will be. So that poses 4 questions, that how to design a biocompatible Coacervate, and whether we can deliver not 1, 2 drugs simultaneously to the cancer cells. And these Coacervates are basically of the micron size order. And generally people say that to deliver a drug, basically we should go for nanomaterials. So can we tune these Coacervates to nano size? And if 2 nano size, can we target those Coacervates to target delivery? Can we use those Coacervates for the target delivery? So to start with objective 1, we have synthesized a Coacervate, complex Coacervate, using electrostatic interaction between zyme and laponite. What is zyme? Zyme is basically a corn protein, corn that we eat. The protein extracted from that, and laponite is basically a clay material, it's silicate clay. It can be natural, it can be artificial, but that is, here we have taken laponite as a silicate system and zyme, and because clay has a negatively charged around it, is water soluble, and zyme is basically a protein which is insoluble in water but soluble in 80% ethanol, which is hydrophobic in nature. So somehow we mix this hydrophobic protein and hydrophilic clay in a mixture of 60:40 water ethanol solution, and we are able to get a Coacervate. And basically we achieve 2 types of Coacervate. So see, this is a Coacervate where you can see this is very dense Coacervate, and this is a Coacervate which is very sparse Coacervate. It depends upon the concentration of the laponite that I've used. So if I've used this concentration of laponite with some typical fixed concentration of zyme, I'll get this dense Coacervate. And if you increase the number of laponite, negatively charged silicate clays, then because of the electrostatic repulsion of the clays, we get a sparse Coacervate. And that we can also see from here. See here, this is a simple interaction where we have a soluble complex, and then at particular concentration where this is zeta potential, this basically signifies the surface charge on the system is almost 0. So if the charge is almost 0, things try to aggregate, and that's why we have got a dense Coacervate. And then because of the repulsion, further addition of laponite, because of the repulsion we have got this sparse Coacervate. And obviously the charges we can see, because repulsion is there, because we can see we have the surface charge started building upon the system. And the typical size of this Coacervate is 1200 nanometer and 800 nanometer diameter. So basically we are in micron size. So whether this micron size can deliver a drug or not. So for that, what we have done, that we know that this zyme is hydrophobic, so we can attach a hydrophobic drug. So in our case, we have taken curcumin as a hydrophobic drug, which generally people use it. And this laponite is basically a clay which has negative charge. So we have attached cisplatin, which is a positively charged drug, is a anti-cancer drug, and we mix these two, and we achieved a system which contains both the properties. The complex contains both the drugs. So if you can, so we have seen that both the drugs could be simultaneously delivered to the cancer cells, and the results indicated. So this is a cell. So this blue staining thing is basically by the nucleus of the cell, which is quite intact. And when we used our Coacervate with drugs, the nucleus fragmented, which means that the death of the cells has already occurred. And this graph is basically suggests that whatever material we have taken, that Coacervate, which is made of hydrophobic cyanide and hydrophilic laponite, is basically biocompatible. See, the percent viability is above 50%. Any concentration, this is very high concentration, whatever concentration you put up a very high concentration, the cell viability is quite good. It's more than 50%. The cell doesn't die. But if you incorporate drug into the system, the cell viability of the cancer goes down. So basically the cell is dying out. If we see the result with in the terms of the actual drug without using the carrier Coacervate, we can see these are the control drugs. The IC50 is very high. See, this is 60. This is for curcumin, and this is 27. That is for this is 34. This 32 for the top one is for cisplatin, and the 60 is for curcumin. And if we combine these drugs through Coacervate, the IC50 value, which is basically the concentration of drugs at which there 50% of the cell dies, has gone down to 21 micromolar of the drug for the, like 21 is to 21. So the concentration of both the drugs, curcumin as well as this is cisplatin, has reduced. So with this concentration of curcumin, and we can achieve the same result which we are achieving individually. So basically there is a combined effect of both the drugs, and both the drugs were successfully transferred to the cancer cells so that it dies. Now the thing that so this is the third objective, that why a small size? A small size because the biological system prefers a small size. The absorption by the cells increases and the toxicity reduces. So can we able to do something to decrease the size, which is of macron size? So what we have done, we have taken the Coacervate, we have added dopamine, and then we added the NOH. So the NOH basically acts as polymerization of the dopamine around the Coacervate. So if see here, when the concentration of where the concentration of this dopamine, sodium hydroxide is very low, the process of polymerization is very low. Process of polymerization is very slow, and that's why bigger particles of Coacervates form. While if the concentration of NOH is very high, we can actually make polymerization around Coacervate, and basically we are covering it with a charged system with dopamine, and we can get a smaller and stable system. So the Coacervate, which was initially very large and of neutral nature, has now become small, and the zeta potential has reduced to -50. Means the system is very stable and the size is small. And dealing with the cancer cell is quite cumbersome. So just to have a quick check whether this system is able to deliver some drug, we have taken gentamicin, which is an antibacterial drug towards E. coli, and we have seen that system actually behaves very good by, these are the zones of inhibition, that how the bacteria is being inhibited, the growth of bacteria is being inhibited around that particular system where we have put my system. And we can also see the IC50, means the growth of those bacteria has reduced, because the drug which is initially gentamicin, pure gentamicin, which is required 15 micromolar to make bacteria die by half of its actual concentration. So the concentration of gentamicin required with our system is almost 1/3, that is 5. So basically the amount of concentration of antibiotic drug is reduced. So basically we are trying to say here that the amount of drug is basically reducing. So with a smaller amount of drug we are achieving same amount of efficiency. And now with this dopamine, we have, because we have dopamine, we have polymerized the system with dopamine, and we are we have chosen two cancer cells, that is colorectal cancer cell and lung cancer cell, which have dopamine. They have dopamine receptors, and we have dopamines with our Coacervate. So if you see that, what we have seen that with that system also, with dopamine system which has a dopamine around it, and the cancer cells and those colorectal cells which have this dopamine receptors, so these dopamine can bind to those dopamine receptors and basically can help in the death of the cells. That's it. So one last point, the main why I have started all this, the only point I wanted to mention is that there are a lot of opportunity in interdisciplinary, for physicists who are doing interdisciplinary, who wanted to do interdisciplinary aspect. So these are the basically typical fields where the students can see their future.
Thank you, Nazmul, for perfectly on time. Questions? Anybody has questions? I have a couple of questions. So you say what is the role of the dopamine? It's always, I think, a binding agent.
Dopamine is there in our body. So we have chosen it because if I'm dealing with the cancer, and few cancer have dopamine receptors. So if the cancer cells have dopamine receptors, the dopamine can efficiently go and bind to that. So targeting will be easy to the cancer cells. Targeting will be very easy. So if I have dopamine receptors, these are dopamine, so dopamine will go and bind to the dopamine receptors and drug will do their job.
And then you talk about this dual drug therapy.
What?
Dual.
So actually, this is a combinatorial drug therapy. Actually, one antibiotic is not working out, so people are using two antibiotics. So this is basically two antibiotic basically are two drugs basically have a synergistic effect. It's like 2 plus 2 is maybe 4. This is called addition, but in biology 2 plus 2 can be 5. Means the combined effect can be larger than the individual effect. So
are they attacking at the same time or one after the other?
no, we are attaching simultaneously both the drugs simultaneously to the one system, and both drugs were delivered simultaneously.
So in the same channel you use, or is there a different channel you are using?
So different?
Different channel you are using to reach to the...
No. Same. These are in vitro experiment, no in vivo experiment. So cells we have on the lab, we have taken cells and we have just added the system to those in vitro cells.
Okay. No more questions. We thank the speaker. And as a part of the acknowledging your presentation, there will be any criticism from the organizing team.
फोटो चाहिए ना उन्हें? This certificate. Oh. This is the Shivaji College motto.
So we will move to the next talk. And next talk will be on this is Srivastava from Day-2 University, Agra.
Okay. And the title will be Preparation and Electrochemical Performance of
marigold petal derived carbon biomass for supercapacitor application.
Good afternoon, everyone, and good afternoon, respected teachers. So, today I am giving my first presentation actually, and my topic is preparations and electrochemical performance of marigold petal derived carbon biomass for supercapacitor application. So, here is the some content, synthesis of the marigold petals, how we are synthesized for that, and what is the biomass and why I am using biomass, and biomass derived carbon from marigold and its application of supercapacitor and result and discussion. So here is the question arise, why we are using biomass. I think so everyone knows about that. Nowadays lithium ion batteries and many batteries are coming in the market. So coming in the market, so that is a chemically reacted, that is a harmful for our environment. So first focus in the environment. So you know very well biomass is a naturally, and it is involved in our naturally in safe for environment also, and is low cost, and it is a environmental friendly natural element composition, and most important thing is waste to energy conversion. As know, we see in our surrounding that we will what we are doing nowadays, everything is going through here and there. Sometimes you are going to temples, so you are go for the temple, and some flowers are putting from here and there. So just I am focusing on this terms. So basically I am using biomass because biomass derived carbon from marigold petals for supercapacitor electrode. So marigold is a natural, and you can collect from temples in function, and you can grow in your homes also. So it is a biomass derived carbon is sustainable, low cost first of all, and eco-friendly, and it have a heteromolecular. It have a naturally oxygen and nitrogen. So when we are understand about the diagram, so we can understand very easily. This is in this figure a natural biomass, different types of biomass are presented in your surroundings. So you see the activated carbon from this carbonization activation carbon. So you see the natural biomass is converted in the activation, recarbonization, carbonization, and after that you make a electrode for the supercapacitor. Nowadays energy is divided in many ways. Energy comes from the, you can say, lithium ion batteries and many other batteries, but now energy storage device, the new era are coming for the supercapacitor. So here is what is the synthesis of the marigold petals. How are you combining, how are you designing, how are you making the carbon. So this is a simple flower. So this is the synthesis. I am collecting from fresh marigold, and after that the grinder and the pre-carbonization 300 degrees centigrade, and after that 800 degrees centigrade, and last I got a carbon as a biomass precursor. And after that it is rich in cellulose and promotes waste to energy conversion. So these are the samples for the marigold. When this is the x-axis for the time and the y-axis for the potential window. So in this diagram, I take a sample is same for the both. So two samples given the voltage of 1 ampere per gram, and second voltage I provided the 6 ampere per gram. So there is the difference between the less current gives the high current voltage storage. So increasing will go the current upward, and decreasing is the voltage down discharge sharply. So motivations come from the, as usual, because now the energy storage and global warming is also going on. So how can we utilize the waste from the converting the main focus for the energy? So this is the eco-friendly, and this is the motivation for the environment concerned and the green energy materials. So, and after that, the applications, as you will see, these are the best applications for the nowadays EV cars and EV electric vehicles is also are coming, because this is the generated, fast generated, sometimes it will break, so it will regenerate itself. So, conclusion of the marigold supports sustainable energy storage. The prepared carbon shows a good electrochemical performance, and these are the references. And now, thank you.
Are there any questions? Anybody has anything?
I think so. This is a very simple concept. So,
You are using marigold to get a biomass.
yes, I am using. Yes.
Simple coal to get coal.
Yes, as you know, coal is now the coal is the natural resources, and coal is coming from the other state also, different types of states. So it is a natural. At sometimes it will मतलब एक टाइम आएगा जब वो बिल्कुल खत्म हो जाएगा. So we have to save for that. So if you are wasting your things, I am not using. I'm using this marigold especially because I am very fascinated for these things. So if you are wasting the materials, you are wasted outside, and this is wasted for the environment situation.
You just said it is of renewable resource, right?
Yes.
The point is, to get a biomass, you need to burn it, and that needs energy. And for that too also you have to use coal or diesel or whatever. So indirectly you are playing with the.
But if you are using coal, other things, right? You are using natural things. So if continuously, how much time you can use it? Sometimes you use your environment from. Sometimes you use plastic things. So sometimes you can use as a carbon, because every natural things you burn it, so it will be converted into carbon. So you can, if these things can use as a carbon, so it gives you a energy storage device also. Okay. Thank you.
Okay, welcome to the last talk of this session. Shivam Sanjay. Shivam will be present on studying solid-state synthesized double peroxide, dysprosium chromium MnO6 for its structural temperature-dependent optical properties.
Thank you, sir. So, hello. Thank you, sir. So, my name is Shubham Sanjay. I am a 4th year student at Department of Physics, Shivaji College, Delhi University. So, I will present my work on double perovskite Day-2 CrMnO6 for its structural and temperature dependent optical properties. So, as you see, perovskites are material with general formula AbO3, where A site is rare earth element and B is transition metal. If we change the B site with two different transition metals, then it will become double perovskites.
So the main structural difference is that in single perovskite we have one B site ion, and in double perovskite we have two different B site ions which enhance its properties. So double perovskites are formed by partial substitution of the B site ion with two different metals, maintaining the charge neutrality and ionic size compatibility. It is important, both types of material are important for ferroelectricity, magnetoresistance. It is important for single perovskite, and for double perovskites we are able to tune its band gap using the B site substitution. Some application of these materials are electronics, energy and sprintonics. Here are some example of single perovskites and double perovskites material. For the preparation, we can prepare it through several methods like solid state reaction, sol gel method and hydrothermal. I have prepared it using solid state reaction method because it is simple, scalable and very cost effective. So here we mix the elements in mortar pestle, we grind it and we put it in hot air oven to remove any humidity and impurity. After that we grind it to increase its homogeneity and we put it for calcination. After calcination we again grind it to regain its homogeneity, and then we make pellets using hydraulic press. After that we sinter it at higher temperature to increase its strength. After that we got the final product. Here we do the X-ray diffraction of the material to confirm its crystal structure. So we got the orthorhombic crystal structure with PBNM symmetry. Here are lattice parameters. The crystalline size is calculated using Williamson Hall plot. It is 56 nanometer. We got a good fit of 1.23 chi-square using Rietveld refinement. After that we do the XPS of the material. Here we got the elemental composition of the material. Here dysprosium is 14%, magnesium is 9%, chromium is 5%. And we also got here the oxidation state of all the elements present here. Using this we got confirmation that our material has been synthesized successfully. After that we do the optical study of the material. Here we calculated the band gap energy. As you can see here, the band gap energy is around 1.16 to 1.28 electron volt. It decreases as temperature increase because of the phonon interactions. After that we do the YP-Wasny fitting to get the value of energy band gap at absolute zero temperature. We got 1.548 electron volt at absolute zero temperature. After that we calculated the Urbach energy of the material and its temperature dependence. As here we can see, as we increase the temperature, the Urbach energy also increases. The value of Urbach energy increases from 1.33 to 1.9 electron volt as we increase the temperature. After that we also calculated the optical conductivity. Here we see optical conductivity has not much effect of temperature. It is very stable at the visible region, visible spectrum region. We calculated the refractive index. It is also very stable and there is no effect of temperature on visible region. As we increase the temperature, the refractive index also increases, which is associated with the phonon interactions and free charge carriers. Skin depth is also calculated using UV visible, and skin depth is very high at the starting, but as we increase the energy, the skin depth also goes stable and there is no much effect of temperature on it. As we see in extinction coefficient, it shows a peak at around 1.5 electron volt, but after increasing the energy it also decreases and there is no much effect of temperature on it. So the conclusion is that we successfully synthesized the material, which is confirmed using XRD and XPS. The structure we got is orthorhombic with PBNM space group. The optical study shows a good band gap of the material. Optical properties also indicates that the refractive index, conductivity, extinction coefficient, skin depth all are very good, which makes it a promising candidate for optoelectronics and functional material applications. I acknowledge the Central University of Haryana for providing the synthesis facilities, USIC University of Delhi for characterization, and Dr. Surendra Kumar, who is the assistant professor at Department of Physics and also my guide, for their support throughout this study. Thank you.
Thank you, Suman, for the talk. Any question? No? Why do you usually develop perovskite this?
Sir, my guide has suggested this material because it has not been studied very much.
Okay. And did you check the composition other than XP?
No, sir. I will do using other techniques. I am currently studying it, sir.
Okay. And then no further questions. Thanks.
Thank you, sir. हो गया ठीक ठाक.
I hope we all had a productive and engaging day. With this, we come to the end of session 5. I would like to thank all our speakers for their insightful presentation and valuable contributions which made this session truly enriching. I would like to extend our heartfelt gratitude to our respected session chair, Dr. Ajit Kumar Patra, for his guidance and for smoothly conducting the session. May I now request Professor Surendra Kumar to kindly felicitate our chairperson, Professor Ajit Kumar Patra, with a token of appreciation. Thank you.
ये सब चेयर पर्सन का है इधर